Okay, so I'm back. One thing I was thinking about is that I said I wanted to do a database, a library, not a database, a library of physical physics equations on Manning, so I can have all these important equations stored somewhere, so I can build systems, try to build systems with them and see what happens. But I realized after that this might someone probably already did that. So it might be worth it to research that. And I think that's something I'm gonna do. But first, well, I also decided that the other course, next course I'm gonna do on Kaggle is Intro to Deep Learning. I'm gonna skip this advanced SQL. Then if I finish all of this and I still want to go back, then I'll go back and do the SQL stuff. But I think it's more important to do the things that are related to what I'm trying to accomplish first. So before I do that, I think I'm gonna keep watching these videos on SQL, finish this video on SQL, or watch it again, maybe. Maybe I'll watch another one. And then I'll watch this video on principal component analysis, which is something I didn't understand very well on the previous Kaggle course.
Breaks it down into bite-sized pieces. Hooray!
And of course, I'm gonna watch it on at least 1.5x speed.
Hello, I'm Josh Starmer and welcome to StatQuest. In this StatQuest, we're going to go through principal component
Maybe
analysis,
2x.
PCA, one step at a time using singular value decomposition, SVD. You'll learn about what PCA does, how it does it, and how to use it to get deeper insight into your data. Let's start with a simple dataset. We've measured the transcription of two genes, gene 1 and gene 2, in 6 different mice. Note, if you're not into mice and genes, think of the mice as individual samples, and the genes as variables that we measure for each sample. For example, the samples could be students in high school and the variables could be test scores in math and reading. Or the samples could be businesses and the variables could be market capitalization and the number of employees. Okay, now we're back to mice and genes because I'm a geneticist and I work in a genetics department. If we only measure one gene, we can plot the data on a number line. Mice 1, 2, and 3 have relatively high values, and mice 4, 5, and 6 have relatively low values. Even though it's a simple graph, it shows us that mice 1, 2, and 3 are more similar to each other than they are to mice 4, 5, and 6. If we measured two genes, then we can plot the data on a two-dimensional XY graph. Gene 1 is the x-axis and spans one of the two dimensions in this graph. Gene 2 is the y-axis and spans the other dimension. We can see that mice 1, 2, and 3 cluster on the right side, and mice 4, 5, and 6 cluster on the lower left-hand side. If we measured three genes, we would add another axis to the graph and make it look 3D, i.e. three-dimensional. The smaller dots have larger values for gene 3 and are further away. The larger dots have smaller values for gene 3 and are closer. If we measure 4 genes, however, we can no longer plot the data. 4 genes require 4 dimensions. Wah wah. So we're going to talk about how PCA can take 4 or more gene measurements, and thus 4 or more dimensions of data, and make a two-dimensional PCA plot. This plot will show us that similar mice cluster together. We'll also talk about how PCA can tell us which gene, or variable, is the most valuable for clustering the data. For example, PCA might tell us that gene 3 is responsible for separating samples along the x-axis. Lastly, we'll talk about how PCA can tell us how accurate the 2D graph is. To understand what PCA does and how it works, let's go back to the dataset that only had 2 genes. We'll start by plotting the data. Then we'll calculate the average measurement for gene 1 and the average measurement for gene 2. With the average values, we can calculate the center of the data.
Also, I found a YouTube channel that I think is really good from what I found from what I saw so far. So I'm probably gonna watch his videos as well. I'm subscribed to him on the other account, but not this
Hello
one.
and
Yeah.
welcome.
So watch a couple of videos of him and I like his style of explanation. Because I was trying to figure some stuff out on the other projects I'm trying to do off stream.
Hello and welcome. I'm James.
Which are all really related somehow, but yeah.
From this point on, we'll focus on what happens in the graph. We no longer need the original data. Now we'll shift the data so that the center is on top of the origin in the graph. Note, shifting the data did not change how the data points are positioned relative to each other. This point is still the highest one, and this is still the rightmost point, etc. Now that the data are centered on the origin, we can try to fit a line to it. To do this, we start by drawing a random line that goes through the origin. Then we rotate the line until it fits the data as well as it can, given that it has to go through the origin. Ultimately, this line fits best. But I'm getting ahead of myself. First, we need to talk about how PCA decides if a fit is good or not. So let's go back to the original, random line that goes through the origin. To quantify how good this line fits the data, PCA projects the data onto it. And then it can either measure the distances from the data to the line and try to find a line that minimizes those distances, or it can try to find a line that maximizes the distances from the projected points to the origin. If those options don't seem equivalent to you, we can build intuition by looking at how these distances shrink when the line fits better, while these distances get larger when the line fits better. Now, to understand what is going on in a mathematical way, let's just consider one data point. This point is fixed, and so is its distance from the origin. In other words, the distance from the point to the origin doesn't change when the red dotted line rotates. When we project the point onto the line, we get a right angle between the black dotted line and the red dotted line. That means that if we label the sides like this, A, B, and C, then we can use the Pythagorean theorem to show how B and C are inversely related. Since A, and thus A squared, doesn't change, if B gets bigger, then C must get smaller. Likewise, if C gets bigger, then B must get smaller. Thus, PCA can either minimize the distance to the line, or maximize the distance from the projected point to the origin. The reason I'm making such a fuss about this is that, intuitively, it makes sense to minimize B and the distance from the point to the line. But it's actually easier to calculate C, the distance from the projected point to the origin, so PCA finds the best fitting line by maximizing the sum of the squared distances from the projected points to the origin. So, for this line, PCA projects the data onto it, and then measures the distance from this point to the origin. Let's call it d sub 1. Note, I'm going to keep track of the distances we measure up here. And then PCA measures the distance from this point to the origin, we'll call that d2, then it measures d3, d4, d5, and d6. Here are all 6 distances that we measured. The next thing we do is square all of them. The distances are squared so that negative values don't cancel out positive values. Then we sum up all these squared distances. And that equals the sum of the squared distances. For short, we'll call this SS distances, or sum of squared distances. Now we rotate the line, project the data onto the line, and then sum up the squared distances from the projected points to the origin. And we repeat until we end up with the line with the largest sum of squared distances between the projected points and the origin. Ultimately, we end up with this line. It has the largest sum of squared distances. This line is called principal component 1, or PC1 for short. PC1 has a slope of 0.25. In other words, for every 4 units that we go out along the gene 1 axis, we go up 1 unit along the gene 2 axis. That means that the data are mostly spread out along the gene 1 axis, and only a little bit spread out along the gene 2 axis. One way to think about PC1 is in terms of a cocktail recipe. To make PC1, mix 4 parts gene 1 with 1 part gene 2. Pour over ice and serve. The ratio of gene 1 to gene 2 tells you that gene 1 is more important when it comes to describing how the data are spread out. Oh no, terminology alert! Mathematicians call this cocktail recipe a linear combination of genes 1 and 2. I mention this because when someone says PC1 is a linear combination of variables, this is what they're talking about. It's no big deal. The recipe for PC1, going over 4 and up 1, gets us to this point. We can solve for the length of the red line using the Pythagorean theorem. The old a squared equals b squared plus c squared. Plugging in the numbers gives us a equals 4.12. So the length of the red line is 4.12. When you do PCA with SVD, the recipe for PC1 is scaled so that this length equals 1. All we have to do to scale the triangle so that the red line is 1 unit long is to divide each side by 4.12. For those of you keeping score, here's the math worked out that shows that all we need to do is divide all 3 sides by 4.12. Here are the scaled values. The new values change our recipe, but the ratio is the same. We still use 4 times as much gene 1 as gene 2. So now we are back to looking at the data, the best fitting line, and the unit vector that we just calculated. Oh no, another terminology alert. This 1 unit long vector, consisting of 0.97 parts gene 1 and 0.242 parts gene 2, is called the singular vector, or the eigenvector for PC1. And the proportions of each gene are called loading scores.
Eigenvector is interesting.
Also, while I'm at it, PCA calls the sums of squares of the distances for the best fit line the eigenvalue for PC1. And the square root of the eigenvalue for PC1 is called the singular value for PC1. Bam, that's a lot of terminology. Now that we've got PC1 all figured out, let's work on PC2. Because this is only a 2-dimensional graph, PC2 is simply the line through the origin that is perpendicular to PC1, without any further optimization that has to be done. And this means that the recipe for PC2 is -1 parts gene 1 to 4 parts gene 2. If we scale everything so that we get a unit vector, the recipe is -0.242 parts gene 1 and 0.97 parts gene 2. This is the singular vector for PC2, or the eigenvector for PC2. These are the loading scores for PC2. They tell us that in terms of how the values are projected onto PC2, gene 2 is 4 times as important as gene 1. Lastly, the eigenvalue for PC2 is the sum of squares of the distances between the projected points and the origin. Hooray! We've worked out PC1 and PC2. To draw the final PCA plot, we simply rotate everything so that PC1 is horizontal. Then we use the projected points to find where the samples go in the PCA plot. For example, these projected points correspond to sample 6. So sample 6 goes here, sample 2 goes here, and sample 1 goes here, etc. Double bam! That's how PCA is done using singular value decomposition. Okay, one last thing before we dive into a slightly more complicated example. Remember the eigenvalues? We got those by projecting the data onto the principal components, measuring the distances to the origin, then squaring and adding them together. We can convert them into variation around the origin by dividing by the sample size minus 1. For the sake of this example, imagine that the variation for PC1 equals 15 and the variation for PC2 equals 3. That means that the total variation around both PCs is 15 plus 3 equals 18. And that means PC1 accounts for 15 divided by 18 equals 0.83, or 83% of the total variation around the PCs. PC2 accounts for 3 divided by 18 equals 17% of the total variation around the PCs. Oh no, another terminology alert. A scree plot is a graphical representation of the percentages of variation that each PC accounts for. We'll talk more about scree plots later. Bam! Okay, now let's quickly go through a slightly more complicated example. PCA with 3 variables, in this case that means 3 genes, is pretty much the same as 2 variables. You center the data. You then find the best fitting line that goes through the origin. Just like before, the best fitting line is PC1. But the recipe for PC1 now has 3 ingredients. In this case, gene 3 is the most important ingredient for PC1. You then find PC2, the next best fitting line, given that it goes through the origin and is perpendicular to PC1. Here's the recipe for PC2. In this case, gene 1 is the most important ingredient for PC2. Lastly, we find PC3, the best fitting line that goes through the origin and is perpendicular to PC1 and PC2. If we had more genes, we just keep on finding more and more principal components by adding perpendicular lines and rotating them. In theory, there is 1 per gene or variable, but in practice, the number of PCs is either the number of variables or the number of samples, whichever is smaller. If this is confusing, don't sweat it. It's not super important, and I'm going to make a separate video on this topic in the next week. Once you have all the principal components figured out, you can use the eigenvalues, i.e., the sums of squares of the distances, to determine the proportion of variation that each PC accounts for. In this case, PC1 accounts for 79% of the variation, PC2 accounts for 15% of the variation, and PC3 accounts for 6% of the variation. Here's the scree plot. PC1 and PC2 account for the vast majority of the variation. That means that a 2D graph, using just PC1 and PC2, would be a good approximation of this 3D graph, since it would account for 94% of the variation in the data. To convert the 3D graph into a 2-dimensional PCA graph, we just strip away everything but the data and PC1 and PC2. Then project the samples onto PC1 and PC2. Then we rotate so that PC1 is horizontal and PC2 is vertical. This just makes it easier to look at. Since these projected points correspond to sample 4, this is where sample 4 goes in our new PCA plot, etc., etc., etc. Double bam! To review, we started with an awkward 3D graph that was kind of hard to read. Then we calculated the principal components. Then, with the eigenvalues for PC1 and PC2, we determined that a 2D graph would still be very informative. Lastly, we used PC1 and PC2 to draw a 2-dimensional graph with the data. If we measured 4 genes per mouse, we would not be able to draw a 4-dimensional graph of the data. Wah wah. But that doesn't stop us from doing the PCA math, which doesn't care if we can draw a picture of it or not, and looking at the scree plot.
You wanna watch another video? This one maybe.
Welcome back. So now we're going to talk about how you can use the singular value decomposition to compute the principal component analysis, or PCA. PCA is the bedrock dimensionality reduction technique for probability and statistics, and it's still very, very commonly used in data science and machine learning applications when you have big data that might have some statistical distribution, and you want to uncover the low-dimensional patterns to build models off of it. PCA has been around for a long time, since 1901 Pearson paper. Okay, so it's a really, really old method, very well established, ton of theory about the statistics of this. And I'm going to essentially pigeonhole this as what we're going to call the statistical interpretation of the SVD. And principal component analysis is in particular going to provide us with a data-driven hierarchical coordinate system. So it gives us a hierarchical that's not how you spell hierarchical, a hierarchical coordinate system, based on data to represent the statistical variations in your data set. Okay, so it's a coordinate system based in terms of directions in your data that capture the maximum amounts of the variance in your data. Okay, and so I'm going to, the notation here is going to be a little different than what we're used to, and that's because the PCA literature and the SVD literature have kind of different conventions about what the matrix looks like. So in the PCA literature, we still have a data matrix X, And it still has a bunch of measurements from experiments, independent experiments. But here we're going to represent those independent experiments as big row vectors, x1, x2, and so on and so forth. Okay, so each row vector x are essentially measurements from a single experiment, measurements from a single experiment. And what we're hoping is that these are kind of individual experiments. So this measurement might be the demographic information from a specific human, age, weight, sex, race, et cetera, et cetera, et cetera. And then x1 would be person 1, x2 is person 2, and so on and so forth. So the same basic idea as before with our data matrix X, except now instead of columns having the information for a specific individual, kind of that measurement from a single experiment, now we're going to have those be rows. And that's because that's consistent with the PCA literature. So I just want to show you how it looks this way. Okay. And the idea here is that we're going to try to find, and we're going to assume that this data X has some statistical distribution. It's not deterministic. There is some statistical variability to this information. And we're going to try to uncover the dominant kind of combinations of features that describe as much of the data as possible. Okay, so we're going to do it using the SVD, but we're going to write it a little bit differently. Okay, so because this is the statistical interpretation of the SVD, there's a few steps that are extra that we don't normally do with SVD that we're going to do here. So kind of step 1 in this procedure is that we're going to compute the mean, the row-wise mean, the average row. So we're going to compute the mean row, and we're just going to call this x bar equals 1 over, I'm going to say that I still have n rows, 1 over n sum of each of these x j's from j equals 1.
Amen.
Okay, so this is the average row. I just average all of the rows. The next thing I'm going to do is I'm going to build an average matrix. So the average matrix is going to be obtained by taking a vector of 1s and multiplying it by that x bar vector. Okay, so I just literally create n copies of x bar, and that's my x bar average matrix. And so step 2 is I'm going to subtract the mean from my data matrix. Okay, so I'm going to subtract the mean. So now I have b equals x minus x bar. And the way we say this in PCA language is that this is the mean-centered data. So if I have some distribution of data where there's some average value to all of this, when I subtract that out, it brings everything down.
I don't understand how it works very well yet. That's why I'm watching this video. I did this course on Kaggle, and they talked about it, but it wasn't
So that the center of
explained really well.
my distribution is at the origin. Okay, so we're going to be modeling this data matrix X, assuming that it is a zero mean Gaussian, and so this is where we subtract off the mean so that it's zero mean. Okay, now what we're going to do is we're going to compute the covariance matrix of this mean-centered data. So the covariance matrix. Again, this is kind of just the correlation matrix from the SVD, but we're calling it a covariance matrix in this context. So the covariance matrix of the rows of B.
How do you define x and y coordinates? The first video the guy explained seemed like a little bit like gradient descent, where you have lines and you're trying to approximate the lines and then finding relationships of these lines, but it still wasn't very clear.
And we're going to call that matrix C. C is equal to B transpose B. Okay, good. So at this point, all we've done is essentially take our data matrix, we've written it in a transpose from how we normally do it. We've subtracted off the mean, and we've computed this correlation matrix or this covariance matrix. So this looks a lot like the X transpose.
Find some vector in this n vector space, that linear combination of some variables that the data changes most. How do you define, how do you plot the data in n dimensions? What would be the x and what would be the y values? How do you decide which relationship you're plotting the data in? Find some vector in this n vector space that linear combination of variables, some variables. Yeah, I'm not sure if I understand.
Transpose X from before, but we've subtracted off the mean. Now what we're going to do is we're going to compute the eigenvectors, the leading eigenvectors of this correlation matrix. And
The
that
dimensions corresponds to the variables you're measuring. For instance, x equals temperature, y. Yeah, but let's say I have 10 dimensions on the data set. What do you do then? So, at least from what I understand right now, it's principal component analysis is about finding the relationship between the features of a data set, which are the dimensions. And then is some mathematical formulation to evaluate this relationship and put it on a number between 1 and -1, I think. But then there's also PCA1, PCA2. There's a bunch of PCs that they called on the Kaggle course. And I don't understand. Maybe the different PCs are the way that each data point relates to each other. That's what's unclear to me still.
That's going to be related both to the singular vectors of x and also to its principal components. Okay, and I'm going to try my best to get the notation and the terminology correct. Again, this is in section 1.5 in our book, so you can go there to refer for more details. Good. So now what we're going to do is we're going to compute the eigendecomposition. We're going to compute the eigenvalues and eigenvectors, so the eigs of C. And in particular, we're going to compute, for example, let's call it V1 transpose B V1. That would be the biggest eigenvector of this matrix B transpose B is V1. Then I would compute V2, then V3, then V4.
So it would be data on the y-axis, let's say, and time on the x-axis. You want to see some relationship between these variables in time. Okay. By A, you mean what? What would be the A? Understand it's one data point, but it's one feature of the data set.
And so on and so forth, just like in the SVD, and there's corresponding eigenvalues just like in the SVD.
Some vector where the data changes the most. Yeah, I'm sorry. I'm lost. Maybe I'm too dumb to, but you say one the first principal component. So go on the second PCA, third PCA. So each PCA is a relationship of two data points, correct? Two different data points. And then the table of PCAs is the collective comparison of all those relationships, you could say. Vector measuring change in data. Yeah, but this change has to be only in relationship to one feature at a time, right? If you're trying to plot it on a graph. Or maximum 2 if you have a 3-dimensional graph. So you can compare, for example, time, pressure, velocity, and acceleration. Let's say you have these 4 dimensions in your data. The first graph would be one of these dimensions measured against time. Or it would be the relationship between two of these dimensions measured across time, something like that. can have n-dimensional graph, doesn't matter. You can have as many variables. But again, it's harder to plot it. Impossible, actually, right? You can only plot, from what I understand, 4 dimensions at most, if you use color as the fourth. Doesn't mean that, of course, there are obviously more dimensions, but to represent in this space-time, you have to be 4 at most. Yeah, that's a good idea, actually. How do you suggest looking for this? Principal component analysis, example 3 variables. How
Hello friends.
how would you define this in the least amount of words possible? Like, what's the point of PCA? From the fundamental first. And what's the difference between PCA and the Pearson correlation, if you know that correlation? Oh, I think on the cargo course they said that Pearson is to find linear relationships between 2 data points, and PCA is to find relationships that are not necessarily linear. Is that correct? And then, if that's the case, I think that the PC 1, 2, 3, 4 is just a comparison of 2 data points at the same time. So the number of PCs is going to be equal to the number of dimensions you have.
In the last video on multivariate analysis, we had seen the introduction of multivariate analysis, some of the important concepts used in it, and the introduction of various tools and techniques as a part of it. In this video, we are going to learn the first tool in multivariate analysis in Minitab software with the help of a practical example for easy understanding and better clarity. So let's begin. Principal component analysis. The principal component analysis is used to identify a smaller number of uncorrelated variables, also called principal components, from a large set of data. With this analysis, you create new variables, also called as principal components, that are linear combinations of the observed variables. The goal of the principal component analysis is to explain the maximum amount of variance with the fewest number of principal components. For example, a bank requires 8 sections of information from loan applicants like income, education level, age, length of the time at current residence, length of time with the current employer, savings, debt, and number of credit cards. A bank administrator wants to analyze this data to determine the best way to group and report it. The administrator collects this information for 30 loan applicants. Here, the administrator performs a principal component analysis to reduce the number.
Oh, they are linear. So they can only So do you know the difference between Pearson and PCA? Because I remember that there is, I think that's how it says, Pearson. Pearson correlation coefficient. Oh, okay. Well, it depends, right? Yeah, it depends in the context of machine learning. Then it depends on the activation function, but without the activation function, I'm not sure if I understand. because to find a relationship with no, well, I don't remember really well how it works. No, just learning this stuff by myself. I did a course on Brilliant on machine learning. That's how I learned. But I'm not really sure how all these ideas are correlated together. Takes time to learn, so just be patient. Yeah, for sure. Thank you. I think I understand, but it's just confusing to just trying to clarify in my mind exactly what I mean by each thing. But the mathematics behind it, I think it's not that difficult. I remember on the course on Brilliant that you can have neural networks that work as a binary. Oh yeah, if you have the binary function as activation, then you're only going to be able to find relationship between the data that can be linearly separable. But if you want to find relationships between data points that are not necessarily linearly separable, then you need a sigmoid activation function because the function has to shape itself differently to found the boundary. So I'm not sure if that's because the equation you said relates to the equation of the weight distribution of the neural networks, which is just one data point times the weight plus the other multiplications. And I'm not sure how this correlates to PCA and Pearson. Pearson correlation, I think, is the linear boundary between data points to find this relationship, but it might be wrong. I'm not sure if that's what it is exactly. And then, to my understanding, PCA was the other way to do that, that increases the accuracy of the relationship between data points. It's mostly related to data analysis, I think. At least that's the course I took when I learned about it. No, I'm a Brazilian. Yeah, both PCA and Pearson correlation are related to data analysis. I don't understand exactly what Pearson's correlation is, but I'm reading a book about machine learning that in this book it says that you should use the Pearson correlation when you're preparing the data for the model to test the model. And that's why I used it, but I still don't understand it really well. And then on the Kaggle course, they also talk about Pearson correlation, but it's not, they don't explain the mathematics of it. They just talk about the libraries and how to use it, and then the numbers already show up. And PCA is the same thing. Yeah. Well, my main thing is trying to prevent AI self-destruction. That's what I'm interested in. And it obviously involves physics, but everything else, and it's probably impossible to do, but I don't see anything else to do, really. If nobody builds stuff to at least increase our chances, then we're probably fucked. So yeah, a little bit. I still don't know the mathematics of it well, but I know just the basic stuff. The concepts I know, but the mathematics, and I've I've stopped. I finished a playlist on special relativity, but around half of the playlist, should to the end of the playlist, I couldn't follow up with the mathematics really well. So yeah, I know. But I was doing mechanical engineering in college, and then I dropped out. So I have a background mathematics. It's not it's not that difficult. It just takes time to understand, because as you increase in complexity, then you need more letters and more ways to put. But it's the same principles are the principles are always the same. Just the way that you're perceiving these principles is different because of the way you're connecting things together. And then they oftentimes do invent some stuff in order to make the logic make sense, like simplify things or put things in different variables. And that's when I start to get lost, because if you're not paying attention, you're probably not going to remember. But all this stuff is pretty much based on math, machine learning as well. Pearson's correlation might have higher validity for a normal distribution of center mean than for a distribution that is normally distributed. Calculus is just about summing small pieces together, integration and finding ratio of small parts. Yeah, but that's the issue, right? Because it goes deeper than that, because then you have to think about philosophy and logic and the epistemology of things. So the tools itself are quite simple, but the implications of them are really hard. That's the problem. Because something like derivatives, for example, in order to really understand them and to, to really know how the things work, you have to understand the principle behind it. And I don't think anyone actually understands how it works, because it involves infinity, and nobody understands what infinity is. So we are building a bunch of stuff, but we don't really understand how it works and the implications of it. And that's why we have the problems we have. You need to know the technical definition of the limit of something means. Yeah, but technical doesn't mean that encapsulates everything. Epsilon delta definition. Are you familiar with that? No? Maybe. I don't know. What is that? Just by name, no. But maybe, yes. It's a normal definition of what taking the limit of some function fr. So is the I studied this a long time ago, but I know that is x divided by x multiplied by something, f of x divided by f of x minus 1 times something there. It's something like that. And when it's basically a mathematical formulation to describe what the value of something becomes, what the function of something becomes once you approach infinity. It actually depends on the value that you're taking the derivative. It can be from zero to, usually it's from 0 to infinity, but it can be from different values, right? And then you find out what happens by substituting the values you're trying to see the differentiation from what I remember. But of course, the proof of these things, and I forgot because I haven't seen them in a long time. But it's basically Pythagoras' theorem for derivation. And for integration is a bunch of formulations with rectangles to fit the function area. But what is the implication of that, right? That's the problem, because what does it exactly mean to take the ratio of change of something? And how are all these variables connected, and why they are connected the way they are? Because mathematics is just logic, and logic is just a consequence of experience. And you can't go beyond knowledge. That's the problem. Because knowledge is already a consequence of experience. So you are defining things in relationship to what you experience, and you can't define where your experience comes from. So the logic from which you're operating can be misaligned with the overall absolute truth of things. So it's always an assumption. That's the problem. Yeah, I think that's what makes a difference, because you can know the technical stuff, but if you don't understand the cause behind them, then the chances are you're not going to be able to use this stuff properly. For every epsilon greater than 0, there exists a delta greater than 0, such that fx minus L smaller than epsilon x minus x delta. All mathematics is based on a set of assumptions called axioms, such as a line is a collection of points from A to B. Yeah, exactly. And then it becomes ridiculous complex out of nowhere.
Number of variables to make the data easier to analyze. The administrator wants enough components to explain at least 90% of the variation in the data. Data considerations for principal component analysis. To ensure that your results are valid, consider the following guidelines when you collect the data, perform the analysis, and interpret your results. In the case of principal component analysis, there is only one requirement of data, and that is you should have at least two variables, and the measurements for each variable should be recorded in separate numeric columns. Example of principal component analysis. Let's continue with the same example. A bank requires 8 sections of information from loan applicants, like:
Are you interested in preventing AI self-destruction or things related to that? Do you have any ideas or suggestions of things that I might be interesting to look on. Brazilian is roughly, it's very similar, but different. It's not exactly the same. French, I've learned French for a little bit, 1 month, and I thought that it was very similar, but yeah, all Latin languages are kind of similar. Then from Brazilian to Spanish, from Portuguese to Spanish is very different. But sometimes if you speak very slowly, you can understand. So Portuguese from Portuguese of Portugal is even more similar, but it's still a little bit different. No, I want to eventually one day. There's so many places to go to.
Income, education level, age, length of time at current residence, length of time with current employer, savings, debt, and the number of credit cards. A bank administrator wants to analyze this data to determine the best way to group and report it.
You should, but you should be careful. Try to come with somebody you know or study the place first. Because depending, it's usually safe, but depending on where you go, of course, can be very, very bad. But it's usually, I wouldn't say my city is dangerous at all. But there's definitely some places where it's almost like a war. On Rio de Janeiro, for example.
The administrator collects this information for 30 loan applicants. Here, the administrator performs a principal component
Yeah, that's the thing. But the issue is, how do you know? No, as a tourist, it's kind of hard to know when you're crossing the line.
analysis to reduce the number of variables to make the data easier to analyze. The administrator wants enough components to explain at least 90%.
It's even worse when you don't speak the language and you're clearly, like, when people can kind of tell you're not from here. Then I think it's become more dangerous because it's an easier target.
Of the variation in the data. Conduct a principal component analysis in Minitab. To conduct a principal component analysis in Minitab, please follow these steps. 1. Enter or copy the data to Minitab worksheet with the data for one variable in one column, as shown in the picture. 2. Select stat, multivariate, and then principal components. 3. In variables, enter C1 to C8. 4. In the number of components to compute, keep the field blank. Here, enter the number of principal components that you want Minitab to calculate. If you have a large number of variables, then you may want to specify a smaller number of components to reduce the amount of output. If you do not know how many components to enter, then variables with higher variances. 6. From the graphs, select the graph you want to see for analysis. Scree plot. Use a scree plot to identify the number of components that explain the most of the variation in the data. Score plot for first two components. Use the score plot to look for clusters, trends, and outliers in the first two principal components. Loading plot for first two components. Use the loading plot to visually interpret the first two principal components. Biplot for first two components. Use the biplot to look for clusters, trends, and outliers through the interpretation of the first two principal components. The biplot overlays the score plot and the loading plot on the same graph. And outlier plot. Use the outlier plot to identify outliers in the data. And 7. Click OK in each dialog box to get the results. We will get the results of analysis in the session window and in graph window. Interpretation of results. In these results, use the cumulative proportion to determine the amount of variance that the principal components explain. Retain the principal components that explain an acceptable level of variance. The acceptable level depends on your application. For descriptive purposes, you may only need 80% of the variance explained. However, if you want to perform other analysis on the data, you may want to have at least 90% of the variance explained by the principal components. This is the case in our example. The first four principal components explain 90.17% of the variation in the data. Therefore, the administrator decides to use these components to analyze the loan applicants. You can also use the size of the eigenvalue to determine the number of principal components. Retain the principal components with the largest eigenvalue, that is greater than 1. The scree plot orders the eigenvalues from largest to smallest. The ideal pattern is a steep curve. followed by a bend and then a straight line. Use the components in the strip curve before the point that starts the line train. The loading plot visually shows the results for the first two components. Age, residence, employee, and savings have large positive loadings on component 1. So, this component measures long-term financial stability. Debt and credit cards have large negative loadings on component 2. So, this component primarily measures an applicant's credit history. With all four of these values. Now to end.
I think this is the last video I watch on this. Maybe this show. Watch this one first and this
All right, in
one.
this presentation,
second.
we'll briefly discuss, and I mean very briefly discuss, principal component analysis. So what is principal component analysis? It's really a good utility to use, or method to use, to explore big data sets or data sets in general. It can be used to create predictive models. It can reduce dimensions to help make sense of data by identifying influential variables in the data. And a really simple example for this might be if we start with a data set that includes household income, zip code, square footage of the house, family size, mailbox color, right? We have all this data and we want to make sense of this data. We don't have any pointed questions, but we just want to kind of see what the data can tell us. We might use principal component analysis, and we might determine that, hey, you know what, household income, family size, and the square foot of the home is sort of related and emerges from the data is important. And then we might also see that the number of pets and the plot size also become important as well in the data. The data set that we use for this particular example was sourced by US Census data, BEA data, and NCHS data. There were 44 data points that were measured, including things like total population, personal income, federal government expenditure, and so on. So high level, what is principal component analysis in terms of a process? The first thing you want to do is review the data. So look for any variables or records that maybe we could exclude. The next step is to use a statistical software package to analyze the data and identify principal components. And then the third step is really to understand the meaning of those principal components and the variables that emerged as significant. Step one, we might want to, again, look at where we can reduce the data on our own without using principal components. In this particular data set, we can see that the data is mostly at a county level, but there were some aggregate rows at the state and at the country level, so we removed those. We also found some data that was incomplete. It was missing a lot of information, and so we also elected to remove those. The second part would be the idea of removing columns or variables that were measured, either because they're duplicates, they're highly correlated to another column, or they're an aggregate or subset of another column. If you look at this particular data set, you can see here there's 6 different variations of population that were included. And so instead of keeping those 6 variations of population, we elected to remove those and keep one variable, which is just general population. You lose some resolution in your data, but for the purposes of what we're doing here, it's sufficient. The next step is to rely on statistical software. So in this case, we use JUMP. We push all of the data into the statistical software and we begin to run a principal component analysis on it. And from this analysis, you can see which components are most prolific. In this case, components 1 and components 2 were retained for our further analysis. The next step is to look at which variables within those components are most significant. You can see on the right here in the factor loading plot that components 2, 72, and 79 were significant and grouped together, and that component 2 was comprised of the variable 73. Identifying the most influential variables, right? So those numbers that we just saw were actually coded variables. So 2 represents resident population, 72 represents manufacturing total value of shipments, 79 represents the federal government expenditure. Those all comprise component 1. Component 2 is comprised of wholesale trade. So that's establishments that fuel the retail sales market. Step 3 is really just considering the meaning of what you've just done. So we've identified 2 components and 4 different variables that comprise those 2 components respectively. The first component was built from population, manufacturing total, and federal government. And these are all things that might be considered economic inputs. Whereas factor 2 was focusing on wholesale trade, which fuels the retail sales market, which might be considered economic outputs. The idea of naming or sort of extrapolating meaning from the components is really more of an art than a science. But it's all about sort of the trends in the data and the information that can be gleaned from it that emerges from this sort of analysis. So in summary, principal component analysis is a really good way to explore data. If you don't have pointed questions, you can kind of see what data or what information emerges from the data. It can help you reduce your data set, and it can also identify significant relationships in and between the data.
I think this stuff is also correlated to special relativity. It's interesting that they use the same name, which is eigenvectors.
If you don't think so, then we have different opinions. Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to be talking about the main ideas behind principal component analysis, and we're going to cover those concepts in 5 minutes. If you want more details than you get here, be sure to check out my other PCA video. Let's say we had some normal cells. Psst! If you're not a biologist, imagine that these could be people, or cars, or cities, or etc. They could be anything. Even though they look the same, we suspect that there are differences. These might be one type of cell, or one type of person, or car, or city, etc. These might be another type of cell. And lastly, these might be a third type of cell. Unfortunately, we can't observe differences from the outside. So we sequence the messenger RNA in each cell to identify which genes are active. This tells us what the cell is doing. Psst, if they were people, we could measure their weight, blood pressure, reading level, etc. Okay, here's the data. Each column shows how much each gene is transcribed in each cell. For now, let's imagine there are only 2 cells. If we just have 2 cells, then we can plot the measurements for each gene. This gene, gene 1, is highly transcribed in cell 1 and lowly transcribed in cell 2. And this gene, gene 9, is lowly transcribed in cell 1 and highly transcribed in cell 2. In general, cell 1 and cell 2 have an inverse correlation. This means that they are probably 2 different types of cells since they are using different genes. Now let's imagine there are 3 cells. We've already seen how we can plot the first 2 cells to see how closely they are related. Now we can also compare cell 1 to cell 3. Cell 1 and cell 3 are positively correlated, suggesting they are doing similar things. Lastly, we can also compare cell 2 to cell 3. The negative correlation suggests that cell 2 is doing something different from cell 3. Alternatively, we could try to plot all 3 cells at once on a 3-dimensional graph. Cell 1 could be the vertical axis, cell 2 could be the horizontal axis, and cell 3 could be depth. We could then rotate this graph around to see how the cells are related to each other. But what do we do when we have 4 or more cells? Draw tons and tons of 2-cell plots and try to make sense of them all? Or draw some crazy graph that has an axis for each cell and makes our brain explode? No, both of those options are just plain silly. Instead, we draw a principal component analysis, or PCA, plot. A PCA plot converts the correlations, or lack thereof, among the cells into a 2D graph. Cells that are highly correlated cluster together. This cluster of cells are highly correlated with each other. So are these, and so are these. To make the clusters easier to see, we can color code them. Once we've identified the clusters in the PCA plot, we can go back to the original cells and see that they represent 3 different types of cells doing 3 different types of things with their genes. Bam! Here's one last main idea about how to interpret PCA plots. The axes are ranked in order of importance. Differences among the first principal component axis, PC1, are more important than differences along the second principal component axis, PC2. If the plot looked like this, where the distance between these 2 clusters is about the same as the distance between these 2 clusters, then these 2 clusters are more different from each other than these 2 clusters. Before we go, you should know that PCA is just one way to make sense of this type of data. There are lots of other methods that are variations on this theme of dimension reduction. These methods include
So each PC
maps,
works in hierarchical order.
T-SNE plots, and multiple dimension scaling plots. The good news is that I've got StatQuest for all of these, so you can check those out if you want to learn more. Note, if the concept of dimension reduction is freaking you out, check out the original StatQuest on PCA. I take it nice and slow so it's clearly explained. Hooray! We've made it to the end of another exciting StatQuest. If you like the StatQuest and want to see more of them, please subscribe. And if you have any ideas for additional
Maybe
StatQuests,
should
well,
watch
put them in the comments below. Until next time, quest on!
the other video again.
StatQuest breaks it down into bite-sized pieces, hooray! Hello, I'm Josh Starmer and welcome to StatQuest. In this StatQuest, we're going to go through principal component analysis, PCA, one step at a time using singular value decomposition, SVD. You'll learn about what PCA does, how it does it, and how to use it to get deeper insight into your data. Let's start with a simple data set. We've measured the transcription of 2 genes, gene 1 and gene 2, in 6 different mice. Note, if you're not into mice and genes, think of the mice as individual samples, and the genes as variables that we measure for each sample. For example, the samples could be students in high school and the variables could be test scores in math and reading. Or the samples could be businesses, and the variables could be market capitalization and the number of employees. Okay, now we're back to mice and genes, because I'm a geneticist and I work in the genetics department. If we only measure one gene, we can plot the data on a number line. Mice 1, 2, and 3 have relatively high values, and mice 4, 5, and 6 have relatively low values. Even though it's a simple graph, it shows us that mice 1, 2, and 3 are more similar to each other than they are to mice 4, 5, and 6. If we measured 2 genes, then we can plot the data on a 2-dimensional XY graph. Gene 1 is the x-axis and spans one of the 2 dimensions in this graph. Gene 2 is the y-axis and spans the other dimension. We can see that mice 1, 2, and 3 cluster on the right side, and mice 4, 5, and 6 cluster on the lower left-hand side. If we measured 3 genes, we would add another axis to the graph and make it look 3D, i.e. 3-dimensional. The smaller dots have larger values for gene 3 and are further away. The larger dots have smaller values for gene 3 and are closer. If we measured 4 genes, however, we can no longer plot the data. 4 genes require 4 dimensions. Wah wah. So we're going to talk about how PCA can take 4 or more gene measurements, and thus 4 or more dimensions of data, and make a 2-dimensional PCA plot. This plot will show us that similar mice cluster together. We'll also talk about how PCA can tell us which gene, or variable, is the most valuable for clustering the data. For example, PCA might tell us that gene 3 is responsible for separating samples along the x-axis. Lastly, we'll talk about how PCA can tell us how accurate the 2D graph is. To understand what PCA does and how it works, let's go back to the dataset that only had 2 genes. We'll start by plotting the data. Then we'll calculate the average measurement for gene 1, and the average measurement for gene 2. With the average values, we can calculate the center of the data. From this point on, we'll focus on what happens in the graph. We no longer need the original data. Now we'll shift the data so that the center is on top of the origin in the graph. Note, shifting the data did not change how the data points are positioned relative to each other. This point is still the highest one, and this is still the rightmost point, etc. Now that the data are centered on the origin, we can try to fit a line to it. To do this, we start by drawing a random line that goes through the origin. Then we rotate the line until it fits the data as well as it can, given that it has to go through the origin. Ultimately, this line fits best. But I'm getting ahead of myself. First, we need to talk about how PCA decides if a fit is good or not. So let's go back to the original, a random line that goes through the origin. To quantify how good this line fits the data, PCA projects the data onto it. And then it can either measure the distances from the data to the line and try to find a line that minimizes those distances, or it can try to find a line that maximizes the distances from the projected points to the origin. If those options don't seem equivalent to you, we can build intuition by looking at how these distances shrink when the line fits better, while these distances get larger when the line fits better. Now, to understand what is going on in a mathematical way, let's just consider one data point. This point is fixed, and so is its distance from the origin. In other words, the distance from the point to the origin doesn't change when the red dotted line rotates. When we project the point onto the line, we get a right angle between the black dotted line and the red
It's pretty much the same thing as gradient descent is
dotted
doing.
line. That means that if we label the sides like this, A, B, and C, then we can use the Pythagorean theorem to show how B and C are inversely related. Since A, and thus A squared, doesn't change, if B gets bigger, then C must get smaller. Likewise, if C gets bigger, then B must get smaller. Thus, PCA can either minimize the distance to the line, or maximize the distance from the projected point to the origin. The reason I'm making such a fuss about this is that, intuitively, it makes sense to minimize B and the distance from the point to the line. But it's actually easier to calculate C, the distance from the projected point to the origin, so PCA finds the best fitting line by maximizing the sum of the squared distances from the projected points to the origin. So, for this line, PCA projects the data onto it, and then measures the distance from this point to the origin. Let's call it d sub 1. Note, I'm going to keep track of the distances we measure up here. And then PCA measures the distance from this point to the origin. We'll call that d2. Then it measures d3, d4, d5, and d6. Here are all 6 distances that we measured. The next thing we do is square all of them. The distances are squared so that negative values don't cancel out positive values. Then we sum up all these squared distances. And that equals the sum of the squared distances. For short, we'll call this SS distances, or sum of squared distances. Now we rotate the line, project the data onto the line, and then sum up the squared distances from the projected points to the origin. And we repeat until we end up with the line with the largest sum of square distances between the projected points and the origin. Ultimately, we end up with this line. It has the largest sum of squared distances. This line is called principal component 1, or PC1 for short. PC1 has a slope of 0.25. In other words, for every 4 units that we go out along the gene 1 axis,
It's not really the same, but principle is similar, but not really the same.
we go up 1 unit along the gene 2 axis. That means that the data are mostly spread out along the gene 1 axis, and only a little bit spread out along the gene 2 axis. One way to think about PC1 is in terms of a cocktail recipe. To make PC1, mix 4 parts gene 1 with 1 part gene 2. Pour over ice and serve. The ratio of gene 1 to gene 2 tells you that gene 1 is more important when it comes to describing how the data are spread out. Oh no, terminology alert! Mathematicians call this cocktail recipe a linear combination of genes 1 and 2. I mention this because when someone says PC1 is a linear combination of variables, this is what they're talking about. It's no big deal. The recipe for PC1, going over 4 and up 1, gets us to this point. We can solve for the length of the red line using the Pythagorean theorem. The old a squared equals b squared plus c squared. Plugging in the numbers gives us a equals 4.12. So the length of the red line is 4.12. When you do PCA with SVD, the recipe for PC1 is scaled so that this length equals 1. All we have to do to scale the triangle so that the red line is 1 unit long is to divide each side by 4.12. For those of you keeping score, here's the math worked out that shows that all we need to do is divide all 3 sides by 4.12. Here are the scaled values. The new values change our recipe, but the ratio is the same. We still use 4 times as much gene 1 as gene 2. So now we are back to looking at the data, the best fitting line, and the unit vector that we just calculated. Oh no, another terminology alert. This 1 unit long vector, consisting of 0.97 parts gene 1 and 0.242 parts gene 2, is called the singular vector, or the eigenvector for PC1. And the proportions of each gene are called loading scores. Also, while I'm at it, PCA calls the sums of squares of the distances for the best fit line the eigenvalue for PC1. And the square root of the eigenvalue for PC1 is called the singular value for PC1. Bam, that's a lot of terminology. Now that we've got PC1 all figured out, let's work on PC2. Because this is only a 2-dimensional graph, PC2 is simply the line through the origin that is perpendicular to PC1, without any further optimization that has to be done. And this means that the recipe for PC2 is -1 parts gene 1 to 4 parts gene 2. If we scale everything so that we get a unit vector, the recipe is -0.242 parts gene 1 and 0.97 parts gene 2. This is the singular vector for PC2, or the eigenvector for PC2. These are the loading scores for PC2. They tell us that in terms of how the values are projected onto PC2, gene 2 is 4 times as important as gene 1. Lastly, the eigenvalue for PC2 is the sum of squares of the distances between the projected points and the origin. Hooray! We've worked out PC1 and PC2. To draw the final PCA plot, we simply rotate everything so that PC1 is horizontal. Then we use the projected points to find where the samples go in the PCA plot. For example, these projected points correspond to sample 6. So sample 6 goes here, sample 2 goes here, and sample 1 goes here, etc. Double bam! That's how PCA is done using singular value decomposition. Okay, one last thing before we dive into a slightly more complicated example. Remember the eigenvalues? We got those by projecting the data onto the principal components, measuring the distances to the origin, then squaring and adding them together. We can convert them into variation around the origin by dividing by the sample size minus 1. For the sake of this example, imagine that the variation for PC1 equals 15 and the variation for PC2 equals 3. That means that the total variation around both PCs is 15 plus 3 equals 18. And that means PC1 accounts for 15 divided by 18 equals 0.83, or 83% of the total variation around the PCs. PC2 accounts for 3 divided by 18 equals 17% of the total variation around the PCs. Oh no, another terminology alert. A scree plot is a graphical representation of the percentages of variation that each PC accounts for. We'll talk more about scree plots later. Bam! Okay, now let's quickly go through a slightly more complicated example. PCA with 3 variables, in this case that means 3 genes, is pretty much the same as 2 variables. You center the data. You then find the best fitting line that goes through the origin. Just like before, the best fitting line is PC1. But the recipe for PC1 now has 3 ingredients. In this case, gene 3 is the most important ingredient for PC1. You then find PC2, the next best fitting line, given that it goes through the origin and is perpendicular to PC1. Here's the recipe for peoples with the number of PC1, and we started with an awkward. In this case, PC1 and PC2 account for 90% of the variation, so we can just use those to draw a 2-dimensional PCA graph. So we project the samples onto the first 2 PCs. These 2 projected points correspond to sample 2. So sample 2 goes here. Bam! Note, if the scree plot looked like this, where PC3 and PC4 account for a substantial amount of variation, then just using the first 2 PCs would not create a variation. If this is confusing, don't sweat it. It's not super important, and I'm going to make a separate video on this topic in the next week. Once you have all the principal components figured out, PCA with 3 variables, in this case that means 3 genes, is pretty much the same as 2 variables. You center the data. You then find the best fitting line that goes through the origin. Just like before, the best fitting line is PC1. But the recipe for PC1 now has 3 ingredients. In this case, gene 3 is the most important ingredient for PC1. You then find PC2, the next best fitting line, given that it goes through the origin and is perpendicular to PC1. Here's the recipe for PC2. In this case, gene 1 is the most important ingredient for PC2.
Oh, so it's in the hierarchy of orders. PC1 is always more important.
PC2. Then we rotate so that PC1 is horizontal and PC2 is vertical.
I
This
think
just
I
makes it easier to look
understand
at. Since these projected points correspond to sample 4, this is where sample 4 goes in our new PCA plot, etc., etc., etc. Double bam! To review, we started with an awkward 3D graph that was kind of hard to read. Then we calculated the principal components. Then, with the eigenvalues for PC1 and PC2, we determined that a 2D graph would still be very informative. Lastly, we used PC1 and PC2 to draw a 2-dimensional graph with the data. If we measured 4 genes per mouse, we would not be able to draw a 4-dimensional graph of the data. Wah wah. But that doesn't stop us from doing the PCA math, which doesn't care if we can draw a picture of it or not, and looking at the scree plot. In this case, PC1 and PC2 account for 90% of the variation, so we can just use those to draw a 2-dimensional PCA graph. So we project the samples onto the first 2 PCs. These 2 projected points correspond to sample 2. So sample 2 goes here. Bam! Note, if the scree plot looked like this, where PC3 and PC4 account for a substantial amount of variation, then just using the first 2 PCs would not create a very accurate representation of the data. Wah wah. However, even a noisy PCA plot like this can be used to identify clusters of data. These
I guess the reason why there's a bunch of PCs is so you get more clear picture of the relationship between all the data points and not just the main ones. But I get it now, I think, how it works. So I'm gonna watch one of these videos about SQL, and then I'm gonna research the stuff on physics.
In this video, you're going to learn the basics of SQL querying in just 15 minutes. And by the time we're finished, you'll be wondering what all the fuss was about. Are you ready? Then let's get started.
I want to research if there is a library for physical equations that I think might be important. And if I don't find it, then I think I'm gonna try to do manning. Yeah, try to set up manning and then watch the playlist. Maybe before that, I think I'm gonna watch the videos related to these topics. And I think I'm not gonna be able to write the equations necessarily, unless the videos have them, but take some notes while I watch these videos, then research the equations, and then start the playlist. On transfers.
Hello and welcome to Vitamin BI, bringing you business intelligence for beginners and beyond. On this channel, I help you do more with data, so if you're new here, consider subscribing. Right, so as I said in my intro, I'm going to teach you the basics of SQL querying, the essentials that you'll need to know if you're considering becoming a business intelligence analyst. Obviously, we can only go so far in 15 minutes, but I promise you that by the time we're finished, you'll be able to understand quite a lot of what you might be called upon to do. We'll be focusing specifically on querying data, not creating or deleting databases, tables, or data, just selecting data from tables that we want to return for our specific needs. Before we get started, let me give you a little context. You might be wondering why you need to learn SQL with BI tools becoming more and more sophisticated. Can't they write the SQL queries for me? The answer to that is yes and no. Yes, when it comes to requesting data for different charts, graphs, and tables that you might want to present in dashboards. In these cases, the BI tool will have some kind of graphical interface to be able to drag and drop fields to return data. But no, in that, in a lot of cases, you'll need to write SQL queries to pre-aggregate, filter, and containing data compiled from the FIFA video game by EA Sports, so soccer stats. I'll leave a link to the database in the description if you want to play around with it too. In terms of the tool I'm using to query the database, it's called Navicat. It's the premium version that allows you to connect to and query pretty much any relational database. But they also have a version for specific RDBMS like MySQL, SQL Server, etc. Link also in the description. Here, we're in the Navicat interface. On the left, we can see that I'm connected to the SoccerDB connection that I've created, and in that connection is a database called main. And in that database, we have various tables: country, league, match, player, etc. We're going to be working mainly with the player table. If I double-click it, we'll see the data contained within that table. We've got 3 different IDs: player name, birthday, height, and weight. What I want to do is write SQL queries and ask the database to return specific data from this table. So I'll open a new query window. Now, when we're asking for data, we're using what's called a select statement. So that's what we need to write first. And if we want to return the whole table in the result, we do so with a star. Then we specify the table that we want to
This
find
stuff
out the field
already
that we want
watched.
separated by commas, like this. Player. But to do this, we would need to put the name in quotes. We could also select. It means that either condition must be met in order for the row to be returned. So that's something we can use a % character after the text to look for, like so. And we get all Aaron's returned. If we wanted to find any player name that ends with Aaron, we put a % character before. Nothing that ends with Aaron. We could put a % before and after, which would basically mean any player name that contains Aaron. And we've got Rolando Aarons. Finally, here's an example which puts the % in the middle of text.
Actually, I just think he's gonna talk about this stuff on the Kaggle course, so
Let's go back to our player table and see how we can sort results. We can do this using the order by clause. The rows are currently sorted by the ID tables. To demonstrate this, I'm going to use the player
it
attribute.
doesn't seem like it gets too complex as well.
But let me show you something even more clever. I showed you earlier how to use the as function to create aliases for fields. Well, we can actually do this for tables as well, which makes the query much cleaner. First, I'm going to give the player aggregator. I'll add this to the overall rating field and run the query. Ah, that's not what we were expecting. But that's because we haven't specified in the query how we want to group the data together. This is when we need to use the group by clause. When we use the group by clause, we need to add into it all of the fields that we need to group. So in this case, essentially all fields. We're going to go one step further and filter this result. To do that, we can use the having clause. The having clause is only applied to the result of the group by function, so isn't the same as the where keyword that's applied before. And it's only applied to numeric values. So in this case, I'm going to ask for only ratings above 85. I need to write it directly after the group by and before the order by. So having rating greater than 85 and run. Only 26 records. And there we have our final query.
So yeah, whatever. I'm gonna start watching the videos on the topics. Maybe this one is not. I'll watch this off stream.
I'm James Murphy from mcoding.io.
Yeah, watch this one first and then the other ones. Oh yeah. First the computation stuff. And this one thing, think I can close. And this is the second topic. So I'm gonna start with this one. I'll be right back.
We're for 9-week weekend programming courses. Today, Brownian motion. If you're watching this video, you've probably heard of Brownian motion before, but the purpose of this video is not so much to tell you what Brownian motion is, but rather to give you a way to simulate it so that you can play with it yourself. Surprisingly, simulating Brownian motion is actually not that difficult. I've already imported NumPy for doing some of the math operations and NumPy for plotting. The first thing that I'm going to do is define the number of time steps that I want to use and my time horizon. So this means that I'm going to be simulating Brownian motion from time 0 to time 1, and I'm going to do so using 10,000 sample points. Next, we'll use numpy.linspace to make the set of times that we're going to use. So linspace takes the initial time, the final time, and the number of sample points. Just for your benefit, let's go ahead and print out times with a small number of time steps so you can see what it's doing. You can see it's just going in uniform increments 0 up until 1. Continuing on, I think the next thing that we're going to need is what is the time step that is between each of those times. So we'll just take times of 1 minus times of 0. The next thing that we need to figure out is how do we actually get values of the Brownian motion? Well, almost the characterizing property of Brownian motion is its independent normally distributed increments. What that means is that if I have Brownian motion at some time t2 and I subtract Brownian motion at some time t1, well then this is a random variable and it's normally distributed with mean 0 and variance t2 minus t1. So instead of trying to find a single formula for the Brownian motion, I'll just generate all of these normally distributed increments and then add them up. So let's make dB, meaning the increments of Brownian motion, the differences between the values of the Brownian motion, that will be a NumPy random normal. And let's give it a shape or size, which is equal to, we're going to need the number of time steps minus 1, because the first one is always going to be 0. Brownian motion starts at 0. Then we need n minus 1 for the rest of the time steps. So by default, this is going to give me mean 0, variance 1. And what I need is variance dt, because we're looking at increments of the Brownian motion, which are in times in this array, all of those times, consecutive times in that array, are separated by a distance of dt from each other. So in order to get a variance of dt, I'll need to multiply by the square root of dt. So let's just do that, numpy square root of dt times that. So dB now is an array of differences of values of Brownian motion. We still haven't constructed any of the values yet, just their differences. To get the actual values of Brownian motion, we'll need to start with its value at 0 and then cumulatively add up the differences. So Brownian motion starts at 0, so let's just use numpy.zeros to create the array, and it takes a shape parameter, and we're just going to have 1, 0 for now. Later on, we're going to be generalizing to simulating multiple Brownian motions, or equivalently, a single multi-dimensional Brownian motion. So if you don't understand why we're choosing to make this 0 an array instead of just a scalar, just keep that in mind that we're going to be generalizing in a little bit. To get the actual values of the Brownian motion, we just need to concatenate the initial value with the cumulative sum of the increments. So I'll take these things to be concatenated. Let's take B0 and the cumulative sum of the increments. And then we can go ahead and just plot it. So we'll plot that. X values are the times and the Y values are the Brownian motion. And then we'll show the plot. So if we did everything correctly, then we should see a plot of Brownian motion. All right, that looks pretty good to me. One thing that I do want to test is I just want to make sure that if we used less time points, that we're still getting the right thing. So I do see that it starts at 0, and it's going around the value -1. Of course, it's random, but the values that you get for Brownian motion shouldn't depend on the number of sample points, but only on the time horizon. So if I go out to t equals 1, it shouldn't matter if I take 10,000 sample points. I should still have something which is around the range plus or minus 1. And you can see, even though it's a totally different sample path, different number of sample points, we do end up around 1. Now, of course, it's possible that that doesn't happen, but it's just the most likely thing is to be in that range, -1 to 1. If you did this experiment and you found that when you increase the number of sample points, that the value of your Brownian motion was increasing, then you probably would have messed up the scaling. So for instance, if I delete this proper scaling by square root of t, and then run the simulation again, so here you can see that by time 1, we're getting values that are up at like 80 and down to -50, almost -60. So if you see that, that should be your clue that Brownian motion doesn't move that much in that amount of time. So if that happens, check your scaling. I'll go ahead and put the proper scaling back in there. Okay, so that's one Brownian motion. What if we want to increase the number of samples? Let's introduce a new parameter d, which is the number of Brownian motions that we're going to simulate all at once. So for now, let's just have, say, 5 Brownian motions. So how can we modify this now? Our times are not going to change because they're all living on the same time axis. Since our times didn't change, our dt doesn't change either. The first thing that actually changes is going to be the increments. So instead of being normally distributed with this size, now we need to just add in a d here. The first coordinate is going to be our time coordinate, and the second coordinate is going to be our either space coordinate, if you're thinking of it as a multi-dimensional Brownian motion, or the index of the Brownian motion, if you're thinking about it as a bunch of independent one-dimensional Brownian motions, which is how it will be drawn when we plot it. Of course, now the initial value of the Brownian motion is going to be 1 by d, because there are d components of it now. Oh, and by the way, if you wanted to consider a Brownian motion that's not started at 0, this is exactly where you would change it. You just put in the numbers that you want there, and then you'll get samples of your Brownian motion started at that place. There are two things that we need to change on this line, namely, now that our dB has more than one dimension to it, we need to specify when we do the cumulative sum and when we do the concatenation what axis we're doing that over. So I know that I want to sum in time, not in space. So I want to sum at the 0 axis, not the 1 axis. So let's change the cumulative sum to axis equals 0. And let's change the concatenation axis to axis equals 0 again. That's because I, again, want to concatenate B0 on as the first time step, not as a spatial dimension. Then we can go ahead and plot it again. So there you have it. It looks like we have a good 5 samples of Brownian motion going. Just for fun, let's bump up the number of Brownian motions and see what it looks like when we do 100. If you've never seen a picture like this, I would encourage you to sit and stare at it for a while. It's a little bit mesmerizing. Even though our Brownian motion was made up of totally independent increments, every single one was just randomly generated, we're starting to see some structure here. Even with 100 sample paths, there's a clear shape that's emerging where the Brownian motion really tends to not go outside of that shape. Let me bump it up to 1,000 here just so we can get a little bit better picture of that shape. Now we see a very defined shape with just a few outliers. Out of 1,000 samples, we have almost a parabolic shape that's emerging. If you're interested in learning about this property, it's actually a very well-known fact. You should look up what's called the law of the iterated logarithm for Brownian motion. It tells you that Brownian motion really tends not to exceed about square root of 2t, and from the name, you can guess that there's a logarithm or 2 hiding in there. But that's not for this video. This just shows that by simulating, you can gain a lot of insight into the statistical properties of a kind of random process like Brownian motion. The last thing that I wanted to show you is another key insight that you can see just by simulating like this. Another characteristic factor of Brownian motion. It has so many interesting properties, but one of them is its quadratic variation. Now, the quadratic variation isn't something that you would probably come up in a video just about Brownian motion. It's more of something that you can look at for a general stochastic process, and it just turns out to have a very interesting formula when you put in Brownian motion. The quadratic variation is not a whole lot more than what it sounds like. Basically, we're just going to take differences of the Brownian motion, square them, and add them. So let's take the numpy difference of the Brownian motion along the axis 0, because remember 0 was for time. And to preserve the original dimensions of the Brownian motion, I'll just go ahead and prepend 0 because the quadratic variation is something that's defined just like Brownian motion to start at 0. Then I'll take those differences and raise them to the power 2. Then I will again use the cumulative sum function so that I can graph them. And again, we'll do this along axis 0, that's the time axis. And then I will just return it. If you didn't quite follow the formulas and dimensions that went into this, just consider the case where d equals 1. Then all the axis stuff disappears, and what you end up having is basically look at the differences of the Brownian motion, take them to the power 2, and add them up. So now, instead of plotting b, let's plot the quadratic variation of b. Huh, that's weird. When you see this picture, you might think that I've done something wrong. Just to be sure that I haven't accidentally messed up the Brownian motion somehow, let's go ahead and plot again, just throw that original plot of b back in. So you can see the Brownian motion is still wiggling all over the place. It has all of the same properties that we were talking about before, but yet this quadratic variation looks like just a line. And indeed, that is the case. The property that I was alluding to earlier is that the quadratic variation of Brownian motion is just t. At time t, Brownian motion has had exactly t quadratic variation. That's why this...
It seems interesting, but I don't think it's worth investigating further so I don't get sidetracked. I think I'm gonna watch these videos now on Turing machines.
Back at the start of the 20th century, mathematicians were fascinated by the question, just how much maths can we do? Not by using our gut feelings or intuitions, but just by following rules very, very carefully, by following an algorithm. In order to make that notion precise, we would have to set out just what do we mean by a program or algorithm. And this is where Alan Turing came in with his notion of a Turing machine. Turing was working on a problem in formal logic, and as part of his proof, he had to come up with a notion of any possible algorithm or any possible machine. He had to come up with a very general way of capturing how algorithms or programs or machines would work. This is where his notion of a Turing machine comes in. The way Turing described these machines goes like this. You have a way of writing down information in a coded form. His way was to think of a tape, which is as long as it needs to be. It's divided up into squares, and on each of these squares there's either a 1 or a 0, or we can have some spaces. Now what our machine does is it looks at the tape one square at a time. So you could imagine it as a little box running above the tape, maybe on little wheels, looking one square at a time. And that information codes up a question or a problem that we want solved. What the Turing machine does is really simple. At any moment in time, it's in a particular state, and it's looking at one square on the tape. And it has a logbook, a program book, and that tells it. If, for instance, you're in state number 23, and you're looking at a 0, then rub out the 0, change it to a 1, move one square to the right, and move into state number 359, for instance. Or, if you're in state number 359 and you're looking at a 1, leave that 1 as it is, move one square to the left, and move into state number 20. Really simple instructions. What the machine does is it starts off with a certain pattern of 1s and 0s. It follows these rules one square at a time, transforming that string of 1 and 0s into a different string of 1s and 0s. And eventually, hopefully, the machine moves into a halting state. It's finished, it's done. And what's left on the tape is the answer to our problem, coded up as 1s and 0s. That is such a simple process, but it turns out it's the essence of computation. Problems. This, when it
that
does,
still doesn't answer anything. Because I don't know how the program runs, how the machine follows the instructions. And I guess it's gonna be through the electric design.
Till now, in this lecture series,
the configuration of logic gates using electricity, but
we have been studying about finite state machines and push-down automata. We have studied about these two machines, and we have also seen the class of languages they accept. And now, as we move one step ahead, we are going to study about the next topic, which is Turing machine. So if you remember, in the very first lecture of this lecture series, this was a diagram we had where we discussed what were the topics that we are going to cover in this lecture series. And if you see, we have already studied about finite state machines and push-down automata. And in finite state machines, we have seen that the class of languages accepted by them is known as the regular languages. And then in push-down automata, the class of languages that was accepted by them was the context-free languages. So we saw the limitations of finite state machines, and we saw how its limitations were overcome by push-down automata because it is more powerful than finite state machines. And now, as we move one step ahead, we are going to study about Turing machine, which is more powerful than finite state machines and also more powerful than the push-down automata. And the class of languages that is accepted by the Turing machines is known as recursively enumerable languages, which can move only to one direction, and that is forward. So we saw the finite state machines and we saw that they had a very limited power and also a very limited memory. And the class of languages accepted by finite state machines are the regular languages, and we already saw what are those regular languages. And coming to push-down automata, in push-down automata, the data structure that we had was the now let
Maybe
us
we
see
should
what's
look
known
at
as
the finite state machines. So I guess this guy has the videos.
Hello everyone, welcome to the next lecture in theory of computation, and in this lecture we will be studying about finite state machines. Alright, so let's get started. So finite state machines, it is also known as finite automata, and this finite automata is divided into two broad categories. The first one being finite automata with output, and the second one being finite automata without
This
output.
guy has a lot of videos. But I can't find the playlist.
Hello everyone.
No, it's a girl. I guess this is just a institute channel, something like that. I'm not sure how. Problem is I don't want to spend too much time on this. There's too many videos. I just want to get the core idea of how it transitioned from the very beginning to the. I think I'm gonna subscribe and then maybe I'll watch some more videos
Recursively
eventually.
enumerable languages, which we will be discussing in detail as we proceed further in this module of Turing machine. Now let us see what we
Actually, this one.
And finite automata with output, we again have two categories, namely Muri machine and Mealy machine. And in finite automata without output, we have three categories, namely deterministic finite automata or DFA, non-deterministic finite automata or NFA, and epsilon non-deterministic finite automata or epsilon NFA. Alright, so in this lecture we will be mainly focusing and studying about our deterministic finite automata or DFA. Okay, so DFA, it stands for deterministic finite automata. Before we start off with DFA, let us remember two important properties of finite state machines that we should always remember, and they are finite state machines, it is the simplest model of computation, and also finite state machines has a very limited memory. So these are two important points that we should always keep in mind before we study anything related to finite state machines. Okay, now we can start off with deterministic finite automata or DFA. Now to make DFA clear, let us take a simple diagram that will make the structure of DFA clear to us. So this diagram here, it shows us the structure of a deterministic finite automata or DFA. So first when you look at this diagram, you may feel confused. What are these? What do we see here? We see some circles labeled as A, B, C, D. We see some edges, some arrows pointing here and there. And we have seen some labelings like 110011. And what are all these? Okay, so I will explain to you what this means so that the structure of this DFA becomes clear to us. So first of all, the first thing that we need to know are states. These circles represented by A, B, C, and D, these circles are known as states. Okay, A, B, C, D are states. And then we see some edges. See, one edge goes from A to B, another edge goes from B to A, and here also we see an edge going from A to C, another from C to A, and here we see one going from C to D, and from D to C, B to D, D to B. So what are these? These edges are actually the transitions. So what does this mean? This transition means that suppose we are in state A, and this edge labeled with 1. This labeling of edges are known as inputs. These are our inputs. So what it means is that when I'm in state A and if I get input 1, if the input I get is 1, so my state A goes from A to B. All right? And in the same way, if I am in state A and if I get input 0, then what happens? State A goes from A to C. Okay? And let's take one more example. Suppose I'm in state C and I get input 1. So where do I go? I go from C to D. And in D, if I get input, say 0, it goes from D to B. So that is how the transition occurs. So these labelings of the edges, they are our inputs and the circles are our states. So it shows how the states transits from one state to another on getting certain inputs. Okay, so that was about the states and the inputs. Now we see that there is something different about state A and state B. So what are they? In state A, we see an arrow that is coming from nowhere and pointing to A. So what is this? This means that A is the starting state or the initial state of this DFA. Whenever you see an arrow coming from nowhere pointing to a state, that shows that that is the initial state or the starting state. And if you look at state D, there is something different. What is that? Every other state has defined using these 5 tuples. Now, the final state is known as F tuples. First of all, we have final state. So what is this table where see over here when there is C and input 1, it goes. So this is the transition function del. It maps from Q cross sigma to Q. So that is how we write the transition function for the DFA. So this was the basic structure of a DFA. I hope you understood it. So these are the main things that you should remember. And this is the structure of the DFA. And we will take some examples in the following.
I'm looking for.
Hello world, I'm Carrie Ann and welcome to Crash Course Computer Science. Over the course of this series, we're going to go from bits, bytes, transistors and logic gates all the way to operating systems, virtual reality and robots. We're going to cover a lot, but just to clear things up, we are not going to teach you how to program. Instead, we're going to explore a range of computing topics in domestic life. Mechanization meant superior harvests and more food, mass-produced goods, cheaper and faster travel and communication, and usually a better quality of life. And computing technology is doing the same right now, from automated farming and medical equipment to global telecommunications and educational opportunities, and new frontiers like virtual reality and self-driving cars. We are living in a time likely to be remembered as the electronic age. And with billions of transistors in just your smartphones, computers can seem pretty complicated, but really they're just simple machines that perform complex actions through many layers of abstraction. So in this series, we're going to break down those layers and build up from simple ones and zeros to logic units, CPUs, operating systems, the entire internet, and beyond. It's just in its infancy, with its biggest impact yet to come. But before we get into all that, we should start at computing's origins, because although electronic computers are relatively new, the need for computation is not. The earliest recognized device for computing was the abacus, invented in Mesopotamia around 2500 BCE. It's essentially a hand-operated calculator that helps add and subtract many numbers. It also stores the current state of the computation, much like your hard drive does today. The abacus was created because the scale of society had become greater than what a single person could keep and manipulate in their mind. There might be thousands of people in a village, or tens of thousands of cattle. There are many variants of the abacus, but let's look at a really basic version, with each row representing a different power of 10. So each bead on the bottom row represents a single unit. In the next row, they represent 10, the row above, 100, and so on. Let's say we have 3 heads of cattle represented by 3 beads on the bottom row on the right side. If we were to buy 4 more cattle, we would just slide 4 more beads to the right for a total of 7. But if we were to add 5 more after the first 3, we would run out of beads. So we would slide everything back to the left, slide 1 bead on the second row to the right representing 10, and then add the final 2 beads on the bottom row for a total of 12. This is particularly useful with large numbers. So if we were to add 1251, we would just add 1 to the bottom row, 5 to the second row, 2 to the third row, and 1 to the fourth row. We don't have to add in our head, and the abacus stores the total for us. Over the next 4,000 years, humans developed all sorts of clever computing devices like the astrolabe, which enabled ships to calculate their latitude at sea, or the slide rule for assisting with multiplication and division. And there are literally hundreds of types of clocks created that could be used to calculate sunrise tides, positions of celestial bodies, and even just the time. Each one of these devices made something that was previously laborious to calculate much faster, easier, and often more accurate. It lowered the barrier to entry, and at the same time amplified our mental abilities. Take note, this is a theme we're going to touch on a lot in this series. As early computer pioneer Charles Babbage said, at each increase of knowledge, as well as on the contrivance of every new tool, human labor becomes a bridge. However, none of these devices were called computers. The earliest documented use of the word computer is from 1613 in a book by Richard Braithwaite. And it wasn't a machine at all, it was a job title. Braithwaite said, "I've read the truest computer of times and the best arithmetician that ever breathed, and he reduceth thy days into a short number." In those days, computer was a person who did calculations, sometimes with the help of machines, but often not. This job title persisted until the late 1800s, when the meaning of computer started shifting to refer to devices. And notable among these devices was a step reckoner built by German polymath Gottfried Leibniz in 1694. Leibniz said, "It is beneath the dignity of excellent men to waste their time in calculation when any peasant could do the work just as accurately with the aid of a machine." It worked kind of like the odometer in your car, which is really just a machine for adding up the number of miles your car has driven. The device had a series of gears that turned. Each gear had 10 teeth to represent the digits from 0 to 9. Whenever a gear bypassed 9, it rotated back to 0 and advanced the adjacent gear by 1 tooth. Kind of like when hitting 10 on that basic abacus. This worked in reverse when doing subtraction too. With some clever mechanical tricks, the step reckoner was also able to multiply and divide numbers. Multiplications and divisions are really just many additions and subtractions. For example, if we want to divide 17 by 5, we just subtract 5, then 5, then 5 again, and then we can't subtract any more 5s. So we know 5 goes into 17 3 times, with 2 left over. The step reckoner was able to do this in an automated way, and was the first machine that could do all 4 of these operations. And this design was so successful, it was used for the next 3 centuries of calculator design. Unfortunately, even with mechanical calculators, most real-world problems required many steps of computation before an answer was determined. It could take hours or days to generate a single result. Also, these handcrafted machines were expensive and not accessible to most of the population. Before the 20th century, most people experienced computing through pre-computated tables, assembled by those amazing human computers we talked about. So if you needed to know the square root of 8,675,309, instead of spending all day hand cranking your step reckoner, you could look it up in a huge book full of square root tables in a minute or so. Speed and accuracy is particularly important on the battlefield, and so militaries were among the first to apply computing to complex problems. A particularly difficult problem is accurately firing artillery shells, which by the 1800s could travel well over a kilometre, or a bit more than half a mile. Add to this varying wind conditions, temperature, and atmospheric pressure, and even hitting something as large as a ship was difficult. Range tables were created that allowed gunners to look up environmental conditions and the distance they wanted to fire, and the table would tell them the angle to set the cannon. These range tables worked so well they were used well into World War II. The problem was, if you changed the design of the cannon or of the shell, a whole new table had to be computed, which was massively time-consuming and inevitably led to errors. Charles Babbage acknowledged this problem in 1822 in a paper to the Royal Astronomical Society entitled Note on the Application of Machinery to the Computation of Astronomical and Mathematical Tables. Let's go to the thought bubble. Charles Babbage proposed a new mechanical device called the difference engine, a much more complex machine that could approximate polynomials. Polynomials describe the relationship between several variables, like range and air pressure, or amount of pizza Cariani eats and happiness. Polynomials could also be used to approximate logarithmic and trigonometric functions, which are a real hassle to calculate by hand. Babbage started construction in 1823, and over the next 2 decades tried to fabricate and assemble the 25,000 components, collectively weighing around 15 tons. Unfortunately, the project was ultimately abandoned. But in 1991, historians finished constructing a difference engine based on Babbage's drawings and writings, and it worked. But more importantly, during construction of the difference engine, Babbage imagined an even more complex machine, the analytical engine. Unlike the difference engine, step reckoner and all other computational devices before it, the analytical engine was a general-purpose computer. It could be used for many things, not just one particular computation. It could be given data and run operations in sequence, it had memory and even a primitive printer. Like the difference engine, it was ahead of its time, and was never fully constructed. However, the idea of an automatic computer, one that could guide itself through a series of operations automatically, was a huge deal and would foreshadow computer programs. English mathematician Ada Lovelace wrote hypothetical programs for the analytical engine, saying a new, a vast, and a powerful language is developed for the future use of analysis. For her work, Ada is often considered the world's first programmer. The analytical engine would go on to inspire arguably the first generation of computer scientists, who incorporated many of Babbage's ideas in their machines. This is why Babbage is often considered the father of computing. Thanks, thought bubble. So by the end of the 19th century, computing devices were used for special purpose tasks in the sciences and engineering, but rarely seen in business, government, or domestic life. However, the US government faced a serious problem for its 1819 census that demanded the kind of efficiency that only computers could provide. The US Constitution requires that a census be conducted every 10 years for the purposes of distributing federal funds, representation in Congress, and good stuff like that. And by 18 machine. His machine was electromechanical. It used traditional mechanical systems for keeping count, like Leibniz's step reckoner, but coupled them with electrically powered components. Hollerith's machine used punch cards, which were paper cards with a grid of locations that could be punched out to represent data. For example, there was a series of holes for marital status. If you were married, you would punch out the married spot. Then when the card was inserted into Hollerith's machine, little metal pins would come down over the card. If a spot was punched out, the pin would pass through the hole in the paper and into a little vial of mercury, which completed the circuit. This now completed circuit powered an electric motor, which turned a gear to add one. In this, the US population was booming, mostly, and it worked. But more importantly, during construction of conditions, temperature, and atmospheric pressure, War II. The problem was, if you changed the design, Babbage acknowledged this problem in 1822 in a paper to the Royal Astronomical Society entitled Note on the Application of Machinery to the Computation of Astronomical and Mathematical Tables. Let's go to the thought bubble. Charles Babbage proposed a new mechanical device called the difference engine, a much more complex machine that could approximate polynomials. Polynomials describe the relationship between several variables, like range and air pressure, or amount of pizza Cariani eats and happiness. Polynomials could also be used to approximate logarithmic and trigonometric functions, which are a real hassle to calculate by hand. Babbage started construction in 1823, and over the next 2 decades tried to fabricate and assemble the 25,000 components, collectively weighing around 15 tons. Unfortunately, the project was ultimately abandoned. But in 1991, historians finished constructing a difference engine based on Babbage's drawings and writings, and it worked. But more importantly, during construction of the difference engine, Babbage imagined an even more complex machine, the analytical engine. Unlike the difference engine, step reckoner, and all other computational devices before it, the analytical engine was a general-purpose computer. It could be used for many things, not just one particular computation. It could be given data and run operations in sequence, it had memory and even a primitive printer. Like the difference engine, it was ahead of its time, and was never fully constructed. However, the idea of an automatic computer, one that could guide itself through a series of operations automatically, was a huge deal and would foreshadow computer programs. English mathematician Ada Lovelace wrote hypothetical programs for the analytical engine, saying a new, a vast, and a powerful language is developed for the future use of analysis. For her work, Ada is often considered the world's first programmer. The analytical engine would go on to inspire arguably the first generation of computer scientists, who incorporated many of Babbage's ideas in their machines. This is why Babbage is often considered the father of computing. Thanks, thought bubble. So by the end of the 19th century, computing devices were used for special purpose tasks in the sciences and engineering, but rarely seen in business, government, or domestic life. However, the US government faced a serious problem for its 1819 census that demanded the kind of efficiency that only computers could provide. The US Constitution requires that a census be conducted every 10 years for the purposes of distributing federal funds, representation in Congress, and good stuff like that. And by 1880, the US population was booming, mostly due to immigration. That census took 7 years to manually compile, and by the time it was completed, it was already out of date. And it was predicted that the 1819 census would take 13 years to compute. That's a little problematic when it's required every decade. The Census Bureau turned to Herman Hollerith, who built a tabulating machine. His machine was electromechanical. It used traditional mechanical systems for keeping count, like Leibniz's step reckoner, but coupled them with electrically powered components. Hollerith's machine used punch cards, which were paper cards with a grid of locations that could be punched out to represent data. For example, there was a series of holes for marital status. If you were married, you would punch out the married spot. Then when the card was inserted into Hollerith's machine, little metal pins would come down over the card. If a spot was punched out, the pin would pass through the hole in the paper and into a little vial of mercury, which completed the circuit. This now completed circuit powered an electric motor, which turned a gear to add one, in this case, to the married total. Hollerith's machine was roughly 10 times faster than manual tabulations, and the census was completed in just 2.5 years, saving the census office millions of dollars. Businesses began recognizing the value of computing and saw its potential to boost profits by improving labor and data-intensive tasks, like accounting, insurance appraisals, and inventory management. To meet this demand, Hollerith founded the Tabulating Machine Company, which later merged with other machine makers lawmakers in 1924 to become the International Business Machines Corporation, or IBM, which you've probably heard of. These electromechanical business machines were a huge success, transforming commerce and government, and by the mid-1900s, the explosion in world population and the rise of globalized trade demanded even faster and more flexible tools for processing data, setting the stage for digital computers, which we'll talk about next week. Crash Course Computer Science is produced in association with PBS.
So basically it started as a collection of mechanical patterns.
Our last episode brought us to the start of the 20th century, where early special-purpose computing devices like tabulating machines were a huge boon to governments and business, aiding and sometimes replacing rote manual tasks. But the scale of human systems continued to increase at an unprecedented rate. The first half of the 20th century saw the world's population almost double. World War I mobilized 17 million people, and World War II involved more than 100 million. Global trade and transit networks became interconnected like never before, and the sophistication of our engineering and scientific endeavors reached new heights. We even started to seriously consider visiting other planets. And it was this explosion of complexity, bureaucracy, and ultimately data that drove an increasing need for automation and computation. Soon, those cabinet-sized electromechanical computers grew into room-sized behemoths that were expensive to maintain and prone to errors. And it was these machines that would set the stage for future innovation. One of the largest electromechanical computers built was the Harvard Mark I, completed in 1944 by IBM for the Allies during World War II. It contained 765,000 components, 3 million connections, and 500 miles of wire. To keep its internal mechanics synchronized, it used a 50-foot shaft running right through the machine, driven by a 5-horsepower motor. One of the earliest uses for this technology was running simulations for the Manhattan Project. The brains of these huge electromechanical beasts were relays, electronically controlled mechanical switches. In a relay, there is a control wire that determines whether a circuit is opened or closed. The control wire connects to a coil of wire inside the relay. When current flows through the coil, an electromagnetic field is created, which in turn attracts a metal arm inside the relay, snapping it shut and completing the circuit. You can think of a relay like a water faucet. The control wire is like the faucet handle. Open the faucet and the water flows through the pipe. Close the faucet and the flow of water stops. Relays are doing the same thing, just with electrons instead of water. The controlled circuit can then connect to other circuits or to something like a motor, which might increment a count on a gear, like in Hollerov's tabulating machine we talked about last episode. Unfortunately, the mechanical arm inside of a relay has mass, and therefore can't move instantly between open and closed states. A good relay in the 1940s might be able to flick back and forth 50 times in a second. That might seem pretty fast, but it's not fast enough to be useful at solving large, complex problems. The Harvard Mark I could do 3 additions or subtractions per second. Multiplications took 6 seconds, and divisions took 15. And more complex operations like a trigonometric function could take over a minute. In addition to slow switching speed, another limitation was wear and tear. Anything mechanical that moves will wear over time. Some things break entirely, and other things start getting sticky, slow, and just plain unreliable. And as the number of relays increases, the probability of a failure increases too. The Harvard Mark I had roughly 3,500 relays. Even if you assume a relay has an operational life of 10 years, this would mean you would have to replace, on average, 140 relay every day. That's a big problem when you're in the middle of running some important multi-day calculation. And that's not all engineers had to contend with. These huge dark and war machines also attracted insects. In September 1947, operators on the Harvard Mark II pulled a dead moth from a malfunctioning relay. Grace Hopper, who we'll talk more about in a later episode, noted, "From then on, when anything went wrong with a computer, we said it had bugs in it." And that's where we get the term computer bug. It was clear that a faster, more reliable alternative to electromechanical relays was needed if computing was going to advance further. And fortunately, that alternative already existed. In 1904, English physicist John Ambrose Fleming developed a new electrical component called a thermionic valve, which housed 2 electrodes inside an airtight glass bulb. This was the first vacuum tube. One of the electrodes could be heated, which would cause it to emit electrons, a process called thermionic emission. The other electrode could then attract these electrons to create the flow of our electric faucet, but only if it was positively charged. If it had a negative or neutral charge, the electrons would no longer be attracted across the vacuum, so no current would flow. An electronic component that permits the one-way flow of current is called a diode. But what was really needed was a switch to help turn this flow on and off. Luckily, shortly after in 1906, American inventor Lee De Forest added a third control electrode that sits between the 2 electrodes in Fleming's design. By applying a positive charge to the control electrode, it would permit the flow of electrons as before. But if the control electrode was given a negative charge, it would prevent the flow of electrons. So by manipulating the control wire, one could open or close the circuit. It's pretty much the same thing as a relay, but importantly, vacuum tubes have no moving parts. This meant there was less wear, and they could switch thousands of times per second. These triode vacuum tubes would become the basis of radio, long-distance telephone, and many other electronic devices for nearly half a century. I should note here that vacuum tubes weren't perfect. They're kind of fragile and can burn out like light bulbs, but they were a big improvement over mechanical relays. Also, initially, vacuum tubes were expensive. A radio set often used just one, but a computer might require hundreds or thousands of electrical switches. But by the 1940s, their cost and reliability had improved to the point where they became feasible for use in computers, at least by people with deep pockets, like governments. This marked the shift from electromechanical computing to electronic computing. Let's go to the thought bubble. The first large-scale use of vacuum tubes for computing was the Colossus Mark I, designed by engineer Tommy Flowers and completed in December of 1943. The Colossus was installed at Bletchley Park in the UK and helped to decrypt Nazi communications. This may sound familiar because 2 years prior, Alan Turing, often called the father of computer science, had created an electromechanical device also at Bletchley Park called the bomb. It was an electromechanical machine designed to break Nazi enigma codes, but the bomb wasn't technically a computer, and we'll get to Alan Turing's contributions later. Anyway, the first version of of Colossus contained 1,600 vacuum tubes, and in total, 10 colossi were built to help with code breaking. Colossus is regarded as the first programmable electronic computer. Programming was done by plugging hundreds of wires into plug boards, sort of like old-school telephone switchboards, in order to set up the computer to perform the right operations. So while programmable, it still had to be configured to perform any specific computation. Enter the Electronic Numerical Integrator and Calculator, or ENIAC, completed a few years later in 1946 at the University of Pennsylvania. Designed by John Muckley and J. Presper Eckert, this was the world's first truly general-purpose programmable electronic computer. ENIAC could perform 5,000 10-digit additions or subtractions per second, many times faster than any machine that came before it. It was operational for 10 years, and it's estimated to have done more arithmetic than the entire human race up to that point. But with that many vacuum tubes, failures were common, and ENIAC was generally only operational for about half a day at a time before breaking down. Thanks, thought bubble. By the 1950s, even vacuum tube-based computing was reaching its limits. The US Air Force's ANFSQ-7 computer, which was completed in 1955, was part of the SAGE Air Defense computer system, which we'll talk about more in a later episode. To reduce cost and size, as well as to improve reliability and speed, a radical new electronic switch was needed. In 1947, Bell Laboratory scientists John Barden, Walter Britton, and William Shockley invented the transistor, and with it, a whole new era of computing was born. The physics behind transistors is pretty complex, relying on quantum mechanics, so we're going to stick to the basics. A transistor is just like a relay or vacuum tube. It's a switch that can be opened or closed by applying electrical power via
And transistors already applied on quantum mechanics. Didn't know that.
control wire. Typically, transistors have two electrodes separated by a material that sometimes can conduct electricity and other times resist it, a semiconductor. In this case, the control wire attaches to a gate electrode. By changing the electrical charge of the gate, the conductivity of the semiconducting material can be manipulated, allowing current to flow or be stopped, like the water faucet analogy we discussed earlier. Even the very first transistor at Bell Labs showed tremendous promise. It could switch between on and off states 10,000 times per second. Further, unlike vacuum tubes made of glass and with carefully suspended fragile components, transistors were solid material, known as a solid-state component. Almost immediately, transistors could be made smaller than the smallest possible relays or vacuum tubes. This led to dramatically smaller and cheaper computers, like the IBM 608, released in 1957, the first fully transistor-powered commercially available computer. It contained 3,000 transistors and could perform 4,500 additions, or roughly 80 multiplications or divisions every second. IBM soon transitioned all of its computing products to transistors, bringing transistor-based computers into offices and eventually homes. Today, computers use transistors that are smaller than 50 nanometers in size. For reference, a sheet of paper is roughly 100,000 nanometers thick, and they're not only incredibly small, they're super fast. They can switch states millions of times per second and can run for decades. A lot of this transistor and semiconductor development happened in the Santa Clara Valley, between San Francisco and San Jose, California. Since the most common material used to create semiconductors is silicon, this region soon became known as Silicon Valley. Even William Shockley moved there, founding Shockley Semiconductor, whose employees later founded Fairchild Semiconductors, whose employees later founded Intel, the world's largest computer chip maker today. Okay, so we've gone from relays to vacuum tubes to transistors. We can turn electricity on and off really fast. But how do we get from transistors to actually computing something, especially if we don't have motors and gears? That's what we're going to cover over the next few episodes. Thanks for watching. See you next week. Crash Course Computer Science.
I think I'm for that part cleared. Now I'm gonna try to understand better transistors, which is just a connection between things, but kind of understand what it is, but I wonder if I can find the mathematics.
In this phone, there are nearly 100 million transistors. In this computer, there's over 1 billion. The transistor is in virtually every electronic device we use. TVs, radios, Tamagotchis. But how does it work? Well, the basic principle is actually incredibly simple. It works just like this switch. So it controls the flow of electric current. It can be off, so you could call that the 0 state, or it could be on, the 1 state. And this is how all of our information is now stored and processed in zeros and ones, little bits of electric current. But unlike this switch, a transistor doesn't have any moving parts, and it also doesn't require a human controller. Furthermore, it can be switched on and off much more quickly than I can flick this switch. And finally, and most importantly, it is incredibly tiny. Well, this is all thanks to the miracle of semiconductors. Or rather, I should say the science of semiconductors. Pure silicon is a semiconductor, which means it conducts electric current better than insulators, but not as well as metals. And this is because an atom of silicon has 4 electrons in its outermost or valence shell. And this allows it to form bonds with its 4 nearest neighbors.
Howdy-ho there.
What's up? So it forms a tetrahedral crystal. But since all these electrons are stuck in bonds, few ever get enough energy to escape their bonds and travel through the lattice. So having a small number of mobile charges is what makes silicon a semiconductor. Now this wouldn't be all that useful without a semiconductor's secret weapon, doping. You've probably heard of doping. It's when you inject a foreign substance in to improve performance. Yeah, it's actually just like that, except on the atomic level. There are two types of doping, called N-type and P-type. To make N-type semiconductor, you take pure silicon and inject a small amount of an element with 5 valence electrons, like phosphorus. This is useful because phosphorus is similar enough to silicon that it can fit into the lattice, but it brings with it an extra electron. So this means now the semiconductor has more mobile charges, and so it conducts current better. In P-type doping, an element with only 3 valence electrons is added to the lattice, like boron. Now this creates a hole, a place where there should be an electron, but there isn't. But this still increases the conductivity of the semiconductor because electrons can move into it. Now, although it's the electrons that are moving, we like to talk about the holes moving around because there's far fewer of
I wonder how this notion changed with quantum mechanics, though. I'm not sure, since she said that was already, when it was invented, was already it already had to do with quantum mechanics. So this notion of the electrons popping from one place to another.
them. Now, since the hole is the lack of an electron, it actually acts as a positive charge. And this is why p-type semiconductor is actually called p-type. The p stands for positive. It's positive charges, these holes, which are moving and conducting the current. Now, it's a common misconception that n-type semiconductors are negatively charged and p-type semiconductors are positively charged. That's not true. They are both neutral because they have the same number of electrons and protons inside them. The n and the p actually just refer to the sign of charge that can move within them. So in n-type, it's negative electrons which can move, and in p-type, it's a positive hole that moves. But they're both neutral. A transistor is made with both n-type and p-type semiconductors. A common configuration has n on the ends with p in the middle.
Just like a switch, a transistor has an electrical contact at each end, and these are called the source and the drain. But instead of a mechanical switch, there is a third electrical contact called the gate, which is insulated from the semiconductor by an oxide layer.
When a transistor is made, the n and p types don't keep to themselves. Electrons actually diffuse from the n-type, where there are more of them, into the p-type to fill the holes. This creates something called the depletion layer. What's been depleted? Charges that can move. There are no more free electrons in the n-type. Why? Because I filled the holes in the p-type. Now this makes the p-type negative thanks to the added electrons. And this is important because the p-type will now repel any electrons that try to come across from the n-type. So the depletion layer actually acts as a barrier, preventing the flow of electric current through the transistor. So right now the transistor is off. It's like an open switch. It's in the zero state. To turn it on, you have to apply a small positive voltage to the gate. This attracts the electrons over and overcomes that repulsion from the depletion layer. It actually shrinks the depletion layer so that electrons can move through and form a conducting channel. So the transistor is now on. It's in the one state. This is remarkable, because just by exploiting the properties of a crystal, we've been able to create a switch that doesn't have any moving parts, that can be turned on and off very quickly just with a voltage. And most importantly, it can be made tiny. Transistors today are only about 22 nanometers wide, which means they're only about 50 atoms across. But to keep up with Moore's law, they're going to have to keep getting smaller. Moore's law states that every 2 years, the number of transistors on a chip should double. And there is a limit. As those terminals get closer and closer together, quantum effects become important, and electrons can actually tunnel from one side to the other. So you may not be able to make a barrier high enough to stop them from flowing. Now, this will be a real problem for the future of transistors, but we'll probably only face that another 10 years down the track. So until then, transistors, the way we know them, are going to keep getting better.
Once you have, let's say, 300 of those qubits,
But I need to study chemistry because
This
I'm not sure what's the current state of chemistry, advanced chemistry, and if it changed much between now and then. Or maybe the questions that I'm trying to look the answer for, probably nobody knows, but it's worth to investigate.
is a transistor, is one of the most important devices ever to be invented. So we're going to learn how they work in detail in this video. Transistors come in many shapes and sizes. There are two main types, the bipolar and the field effect. We're going to mostly focus on the bipolar version in this video. Transistors are small electronic components with two main functions. It can act as a switch to control circuits, and they can also amplify signals. Small, low-power transistors are enclosed in a resin case to help protect the internal parts, but higher-power transistors will have a partly metal case, which is used to help remove the heat which is generated, as this will damage the components over time. We usually find these metal body transistors attached to a heatsink, which helps remove the unwanted heat. For example, inside this DC bench power supply, we have some MOSFET transistors, which are attached to very large heatsinks. Without the heatsink, the components quickly reach 45 degrees Celsius, or 113 degrees Fahrenheit, with a current of just 1.2 amps. They will become much hotter as the current increases. But for electronic circuits with small currents, we can just use these resin body transistors, which do not require a heatsink. On the body of the transistor, we find some text. This will tell us the part number, which we can use to find the manufacturer's datasheet. Each transistor is rated to handle a certain voltage and current, so it's important to check these sheets. Now, with a transistor, we have 3 pins, labeled E, B, and C. This stands for the emitter, the base, and the collector. Typically, with these resin body type transistors with a flat edge, the left pin is the emitter, the middle is the base, and the right side is the collector. However, not all transistors use this configuration, so do check the manufacturer's datasheet. We know that if we connect a light bulb to a battery, it will illuminate. We can install a switch into the circuit and control the light by interrupting the power supply. But this requires a human to manually control the switch. So how can we automate this? For that, we use a transistor. This transistor is blocking the flow of current, so the light is off. But if we provide a small voltage to the base pin in the middle, it causes the transistor to start allowing current to flow in the main circuit. So the light turns on. We can then place a switch on the controlling pin to operate it remotely, or we can place a sensor on this to automate the control. Typically, we need to apply at least 0.6 to 0.7 volts to the base pin for the transistor to turn on. For example, this simple transistor circuit has a red LED and a 9-volt power supply across the main circuit. The base pin is connected to the DC bench power supply. The circuit diagram looks like this. When the supply voltage to the base pin is 0.5 volts, the transistor is off, so the LED is also off. At 0.6 volts, the transistor is on, but not fully. The LED is dim because the transistor is not yet letting the full current flow through the main circuit. Then, at 0.7 volts, the LED is brighter because the transistor is letting almost the full current through. And at 0.8 volts, the LED is at full brightness. The transistor is fully open. So what's happening is we're using a small voltage and current to control a larger voltage and current. We saw that a small change to the voltage on the base pin causes a large change on the main circuit. Therefore, if we input a signal to the base pin, the transistor acts as an amplifier. We could connect a microphone which varies the voltage signal on the base pin, and this will amplify a speaker in the main circuit to form a very basic amplifier. Typically, there is a very small current on the base pin, perhaps just 1 milliamps or even less. The collector has a much higher current, for example 100 milliamps. The ratio between these two is known as the current gain, and uses the symbol beta. We can find the ratio in the manufacturer's datasheet. In this example, the collector current is 100 milliamps, and the base current is 1 milliamp. So the ratio is 100 divided by 1, which gives us 100. We can also rearrange this formula to find the currents also. We have two main types of bipolar transistors, the NPN and the PNP type. The two transistors look nearly identical, so we need to check the part number to tell which is which. With an NPN transistor, we have the main circuit and the control circuit. Both are connected to the positive of the battery. The main circuit is off until we press the switch on the control circuit. We can see the current is flowing through both wires to the transistor. We can remove the main circuit, and the control circuit LED will still turn on when the switch is pressed, as the current is returning to the battery through the transistor. In this simplified example, when the switch is pressed, there are 5 milliamps flowing into the base pin. There are 20 milliamps flowing into the collector pin, and 25 milliamps flowing out of the emitter. The current therefore combines in this transistor. With a PNP transistor, we again have the main circuit and the control circuit, but now the emitter is connected to the positive of the battery. The main circuit is off until we press the switch on the control circuit. We can see with this type that some of the current flows out of the base pin and returns to the battery. The rest of the current flows through the transistor and through the main LED and then back to the battery. If we remove the main circuit, the control circuit LED will still turn on. In this example, when the switch is pressed, there are 25 milliamps flowing into the emitter, 20 milliamps flowing out of the collector, and 5 milliamps flowing out of the base. The current therefore divides in this transistor. I'll place these side by side so you can see how they compare. Transistors are shown on electrical drawings with symbols like these. The arrow is placed on the emitter. The arrow points in the direction of conventional current, so that we know how to connect them into our circuits. To understand how a transistor works, I want you to first imagine water flowing through a pipe. It flows freely through the pipe until we block it with a disc. Now, if we connect a smaller pipe into the main one and place a swing gate within this small pipe, we can move the disc using a pulley. The further the swing gate opens, the more water is allowed to flow in the main pipe. The swing gate is a little heavy, so a small amount of water won't be enough to open it. A certain amount of water is required to force the gate to open. The more water we have flowing in this small pipe, the further the valve opens and allows more and more water to flow in the main pipe. This is essentially how an NPN transistor works. You might already know that when we design electronic circuits, we use conventional current. So in this NPN transistor circuit, we assume that the current is flowing from the battery's positive into both the collector and the base pin, and then out of the emitter pin. We always use this direction to design our circuits. However, that's not what's actually occurring. In reality, the electrons are flowing from the negative to the positive of the battery. This was proved by Joseph Thomson, who carried out some experiments to discover the electron and also proved they flowed in the opposite direction. So, in reality, electrons flow from the negative into the emitter and then out of the collector and the base pin. We call this electron flow. I'll place these side by side so you can see the difference in the two theories. Remember, we always design circuits using the conventional current method. But scientists and engineers know that electron flow is how it actually works. By the way, we have also covered how a battery works in detail in our previous video. Do check that out, links can be found in the video description down below. Okay, so we know that electricity is the flow of electrons through a wire. The copper wire is the conductor and the rubber is the insulator. Electrons can flow easily through the copper, but they can't flow through the rubber insulator. If we look at this basic model of an atom of a metal conductor, we have the nucleus at the center, and this is surrounded by a number of orbital shells which hold the electrons. Each shell holds a maximum number of electrons, and an electron needs to have a certain amount of energy to be accepted into each shell. The electrons located furthest away from the nucleus hold the most.
This view doesn't make sense to me. And I still don't understand how do you go from that to a program. I guess what's happening is every time you type something on the keyboard or you move a mouse, there is a gate that is closed on the computer through the input, but I'm not sure. I know that the mouse is the laser that There's a video on bench education about this, but I'm not really sure if that's exactly
energy.
how it works.
The outermost shell is known as the valence shell. A conductor has between 1 and 3 electrons in its valence shell. The electrons are held in place by the nucleus, but there is another shell known as the conduction band. If an electron can reach this, then it can break free from the atom and move to other atoms. With a metal atom, such as copper, the valence shell and the conduction band overlap, so it's very easy for the electrons to move. With an insulator, the outermost shell is packed. There's very little to no room for an electron to join. The nucleus has a tight grip on the electrons, and the conduction band is far away, so the electrons can't reach this to escape. Therefore, electricity cannot flow through this material. However, there's another material known as a semiconductor. Silicon is an example of a semiconductor. With this material, there's one too many electrons in the valence shell for it to be a conductor, so it acts as an insulator. But as the conduction band is quite close, if we provide some external energy, some electrons will gain enough energy to make the jump into the conduction band and become free. Therefore, this material can act as both an insulator and a conductor. Pure silicon has almost no free electrons, so what engineers do is dope the silicon with a small amount of another material, which changes its electrical properties. We call this p-type and n-type doping. We combine these materials to form the p-n junction. We can sandwich these together to form an NPN or a PNP transistor. Inside the transistor, we have the collector pin and the emitter pin. Between these, in an NPN transistor, we have 2 layers of n-type material and 1 layer of p-type. The base wire is connected to the p-type layer. In a PNP transistor, this is just configured the opposite way. The entire thing is enclosed in a resin to protect the internal materials. Let's imagine the silicon hasn't been doped yet, so it's just pure silicon inside. Each silicon atom is surrounded by 4 other silicon atoms. Each atom wants 8 electrons in its valence shell, but the silicon atoms only have 4 electrons in their valence shell, so they sneakily share an electron with their neighboring atom to get the 8 they desire. This is known as covalent bonding. When we add the n-type material, such as phosphorus, it will take the position of some of the silicon atoms. The phosphorus atoms have 5 electrons in their valence shell, so as the silicon atoms are sharing electrons to get their desired 8, they don't need this extra one, which means there's now extra electrons in the material, and these are free to move around. With p-type doping, we add in a material such as aluminium or aluminum. This atom has only 3 electrons in its valence shell. It therefore can't provide its 4 neighbors with an electron to share, so one of them will have to go without. This means a hole has been created where an electron can sit and occupy. We now have 2 doped pieces of silicon, one with too many electrons and one with not enough electrons. The 2 materials join to form a p-n junction. At this junction, we get what's known as a depletion region. In this region, some of the excess electrons from the n side will move over to occupy the holes in the p side. This migration will form a barrier with a buildup of electrons and holes on opposite sides. The electrons are negatively charged, and the holes are therefore considered positively charged. So this buildup causes a slightly negatively charged region and a slightly positively charged region. This creates an electric field and prevents more electrons from moving across. The potential difference across this region is typically around 0.7 volts. When we connect a voltage source across the 2 ends, with the positive connected to the p-type material, this will create a forward bias, and the electrons will begin to flow. The voltage source has to be greater than the 0.7 volt barrier, otherwise electrons cannot make the jump. When we reverse the power supply so that the positive is connected to the n-type material, the electrons held in the barrier will be pulled back towards the positive terminal and the holes will be pulled back towards the negative terminal. This has caused a reverse bias. In a NPN transistor, we have 2 layers of n-type material. So we have 2 junctions and therefore 2 barriers, so no current can flow through it ordinarily. The emitter n-type material is heavily doped, so there are a lot of excess electrons here. The base p-type is lightly doped, so there are a few holes here. The collector n-type is moderately doped, so there are a few excess electrons here. If we connect a battery across the base and the emitter with the positive connected to the p-type layer, this will create a forward bias. The forward bias causes the barrier to collapse as long as the voltage is at least 0.7 volts. So the barrier diminishes and the electrons rush across to fill the space within the p-type material. Some of these electrons will occupy a hole, and they will be pulled towards the positive terminal of the battery. The p-type layer is thin and was lightly doped on purpose, so that there is a low chance of electrons falling into a hole. The rest will remain free to move around the material. Therefore, only a small current will flow out of the base pin, leaving an excess of electrons now in the p-type material. If we then connect another battery between the emitter and the collector, with the positive connected to the collector, the negatively charged electrons within the collector will be drawn to the positive terminal, which causes a reverse bias. If you remember, with a reverse bias, the electrons and holes of the barrier are pulled back across. So the electrons on the p-type side of the barrier are pulled across to the n-type side, and the holes on the n-type side are pulled back to the p-type side. There are already an excess number of electrons in the p-type material, so they will move to occupy these holes, and some of them will be pulled across, because the voltage of this battery is greater, so the attraction is much higher. As these electrons are pulled across, they flow into the battery, so a current develops across the reverse bias junction. A higher voltage on the base pin fully opens the transistor, which means more current and more electrons moving into the p-type layer. Therefore, more electrons are pulled across the reverse bias. We also see more electrons flowing in the emitter side of the transistor compared to the collector side. Okay, that's it for this video, but to continue learning about electronics engineering, click on one of the videos on screen.
And it's still not sufficient. Still not.
The invention of transistors revolutionized human civilization like no other technology.
Just that I think all the explanations are gonna be pretty much like that. And I think that this might not be exactly how it works. in practice. But I don't know if I can find on YouTube a channel that explains more deeper stuff, or if it even exists already.
Technology.
I assume it does, but I'm not sure where to find it.
At the heart of a smartphone lies a processor, and this processor holds about 2 billion transistors. What do these incredibly tiny devices do? How do they work? Transistors can act like a switch with no moving parts. They can amplify a weak signal. In fact, amplification is the basic function of a transistor. First, let's understand the basis of transistors. We will come back to the application part later. Transistors are made of semiconductors such as silicon. Each silicon atom is bonded with 4 neighboring silicon atoms. Silicon has 4 electrons in its valence shell. Let's replace the silicon atom with a 4-handed smiley. Each hand holds 1 electron. Each one of these electrons goes for sharing with a neighboring silicon atom. This is known as a covalent bond. Currently, the electrons are in their valence band. If the pure silicon has to conduct electricity, the electrons have to absorb some energy and become free electrons. Thus, the pure silicon will have a low electrical conductivity. A technique called doping is used to improve the conductivity of semiconductors. For example, say you inject phosphorus with 5 valence electrons. Here, 1 electron will be free to move in the system. This is known as N-type doping. On the other hand, if you inject boron with 3 valence electrons, there will be a vacant position for an electron. This vacant position is known as a hole, and a neighboring electron can fill this hole at any time. This electron movement is visualized as holes moving in opposite direction. We call this P-type doping. If you dope a silicon wafer in the following manner, a transistor is born. But if you really want to understand how a transistor works, we have to get a clear idea of what happens at the electron level of a more basic component, a diode. A diode is formed when you dope one part of silicon as a P-type and the other part as an N-type. Something very interesting happens at the boundary of the N and P joint. The abundant electrons on the N side will have a natural tendency to migrate to the holes that are available on the P side. This will make the P side boundary slightly negatively charged and the N side slightly positively charged. The resulting electric field will oppose any further natural migration of the electrons. If you apply an external power source across the diode as shown, the power source will attract the electrons and holes. Electricity flow is impossible in this case. However, if you reverse the power connection, the situation is quite different. Assume that the power source has enough voltage to overcome the potential barrier. You can immediately see that the electrons will be pushed away by the negative terminal. When the electrons cross the potential barrier, they will be drained of energy and will easily occupy the holes in the P region. But due to the attraction of the positive terminal, these electrons can now jump to the holes nearby in the P region and flow through the external circuit. This is known as the forward biasing of a diode. Just keep this simple principle of a diode in mind. You will understand the operation of a transistor very easily. Now, back to the transistor. Note that the P layer is really thin and lightly doped. You can easily see that the transistor is essentially 2 diodes sandwiched back to back. So, whichever way you connect the power source, one diode will always be reverse biased and block the electricity flow. This means the transistor is in the off state. Now, let's connect the second power supply as shown. The power supply should have enough voltage to overcome the potential barrier. So, this is just a forward biased diode. Thus, a high number of electrons will be emitted from the N region. Just like in a diode, a few electrons will combine with the
Same thing.
So this right here is a bipolar junction transistor, which is a pretty common kind of transistor. And this particular one is an NPN transistor. And so this transistor is made up of 3 layers of silicon, like this. And maybe you can guess what it means for it to be an NPN transistor. These 2 layers of silicon are N-type, and this layer here is P-type, NPN. And if you haven't watched my previous video where I go into quite a bit of detail about what these N-type and P-type silicon is, you should definitely go back and watch that. Otherwise, the rest of this isn't going to make a whole ton of sense. And so this is an NPN transistor, and they make PNP transistors as well, but we'll just talk about NPN for now. And so this here is the circuit diagram for a transistor, and it's got the 3 leads coming off of it. There's a emitter, a base, and a collector. And if you look at the actual physical transistor, there's 3 leads coming off, and this is the emitter, the middle one is the base, and this is the collector, although that's not really standardized, but in this particular case, that's how it works. And what a transistor does is it is a current-controlled switch. And so what that means is that if we establish a small current from the base to the emitter in this direction, the transistor will switch on, and it will allow a very large current to flow from the collector to the emitter. And sometimes you can also use this as an amplifier because a small current is amplified into a large current flow here. And so first off, there's actually something kind of confusing about the way this diagram is drawn with this arrow like this, which is that in a circuit diagram, and a lot of times a lot of engineers like to think about positive current flow, which is current flowing from positive to negative, when in reality it's the electrons that flow from negative to positive. And it doesn't really matter which convention we use because, as long as there's current flowing in one direction or the other, the current will have the same effect. But when we start to actually look at what's going on inside the transistor, it's easier to think of this in terms of the direction the electrons are flowing instead of the conventional direction. And so really what's going on here, even though the arrow is pointing this way, we think of current flowing that way, in reality the electrons are flowing from the emitter to the base. And so we'll just turn all this around for this discussion here. And so to kind of restate what it is that the transistor does in terms of electron flow is that a small flow of electrons from the emitter to the base will turn the transistor on and allow a large flow of electrons from the emitter to the collector. So if we look at it in this scenario, this piece of N-type material might be the emitter. This middle P-type is the base, and then this N-type material over here is the collector. And so what we're going to do with the transistor is that we're going to try to put a bunch of electrons in over on this side, and we want to get them out over on this side, but if the transistor is off, then we're not going to get that current flow. And in order to turn the transistor on, what we want to do is get a small current flowing through the emitter and further free electrons into here. This is going to become here, the diode, and we now have free to move around NP. If the space were really attracted to this,
I think I have enough of this.
world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon foundation is what gives each Intel chip limitless potential. At the heart of all modern electronics, the transistor is a tiny switch, 10,000 times smaller than a human hair, that controls the flow of electrons through a circuit. To build a processor, billions of transistors are packed into an area no larger than a fingernail. It's one of mankind's most complex feats, and a remarkable achievement that Intel has essentially doubled transistor density in every new generation of processors. The process begins when silicon-rich sand is melted and cooled, forming a solid, which is then sliced into wafers. Once in
This is good.
most complex feats, and a remarkable achievement that Intel has essentially doubled transistor density in every new generation of processors. The process begins when silicon-rich sand is melted and cooled, forming a solid, which is then sliced into wafers. Once inside an Intel fab, the raw wafers begin their long journey through an incredibly complex process. They're loaded into front-opening unified pods, or FOUPs, which travel hundreds of miles along Intel's automated superhighway, going from tool to tool, as processors are painstakingly built up on each wafer. The wafer first goes through a series of important steps, such as photolithography, ion implantation, and etching, that prepare it for the critical transistor formation process. Intel was the first to manufacture three-dimensional transistors called FinFETs. FinFET construction requires first building a channel in the form of a fin. Intel has devised several innovations to overcome fundamental barriers to continued transistor scaling. One such innovation is a breakthrough fabrication method called gate last. It involves building, then removing a temporary gate.
I think I'm also gonna search for this.
In order to precisely place the dielectric material and metal gate. This allows for the gate to wrap around the fin and control the flow of electrons through the channel. Another invention moves the transistor contact directly over the active gate. To accomplish this, the gate material is recessed and then filled with insulating dielectric material to prevent the creation of a short circuit. Next, the dielectric near the gate is etched, filled with metal, recessed, and capped to allow a novel self-aligning process that enables the high-density contact geometries. Now, the dielectrics are etched selectively to expose only the desired part to connect to the first metal lines. This is done through an innovative via etch and deposition scheme, allowing contact over active gate to happen. Finally, dozens of layers of metal interconnect lines are added to complete the circuit. After more than 1,000 of these complex steps, the wafers are finally prepared for singulation and packaging. Innovative processor packaging has become a critical feature of advanced computing architecture. 2D and 3D packaging technologies are enabling new device form factors and additional boosts in performance and energy efficiency. Testing of the final product ensures that every chip exceeds our performance and quality standards. In addition to adding more performance and features with each new processor generation,
If they know it at all, most people know Silicon from the valley in California that bears its name, the birthplace of modern computing, where technological dreams became reality, where brilliant 20-somethings became millionaires. So we chemists know silicon first and foremost as the most abundant element in the Earth's crust. Oxides of silicon, known as silicates, make up sand, which covers not only every desert and shoreline on the Earth, but also most of the ocean floor. Silicates also include quartz and most types of clay, and they're found in living things like little spikes and nettles, and as a polishing agent in toothpaste. It's everywhere. And, of course, because of their uniquely wonderful chemical properties, crystals of elemental silicon form the basis of semiconductors. These crystals can be combined to make diodes and transistors, acting essentially as chemical on-off switches that make binary code, and therefore computers possible. Fascinatingly enough, only a few minor differences in atomic arrangement allow an element found on the bottom of the ocean to make the computer that you're watching me on possible. As with carbon, everything comes down to the network these atoms form. Once you learn the chemistry of these different networks, you'll come to understand why glass is glass and clay is clay. You'll understand what chemists mean when they talk about doping, and you'll finally get why a valley in California is named for arguably one of the most intriguing elements in the universe. Are basically the same thing, just with the atoms arranged a little differently. The chemical name of this substance is silica, made up of silicon and oxygen in a 1:2 ratio. For that reason, we say that the chemical formula of silica is SiO2, even though it doesn't actually exist in separate individual molecules. Like graphite and diamond, the two forms of pure carbon, silicon and its oxides are network solids. And also like graphite and diamond, the different forms that they take are all about bonding differences. The form of the silica that makes sand is exactly the same as the form that comprises quartz. In fact, the silica in sand is basically just tiny bits of quartz. Silica structure is based on a tetrahedral arrangement of a silicon atom bonded to 4 oxygen atoms. That's right, 4, not 2. The trick is that each of the oxygen atoms can form 2 bonds, so they also bond to another silicon atom on the other side. So each silicon is bonded to 4 oxygens, while each oxygen is bonded to 2 silicons. Si2O4 4 simplifies to SiO2, and that's where we get the formula. As the molecule continues to build on itself, it can make various crystal structures depending on the orientation of the little tetrahedrons. These are different forms of quartz, clays, and other minerals. They can make two-dimensional forms as sheets or three-dimensional crystals, and each form has its own properties and behaviors. Ceramics and other clays get their strength from the two-dimensional types. When the clay is wet, silica sheets move around freely in the clay, and as it dries, they move closer to each other and bond together, forming a rigid framework. This resulting composite is extremely hard and heat-resistant. Both of these properties make ceramics useful at tons of ways, which you've probably been exploring since you were a toddler and got your first box of modeling clay. Three-dimensional silicates can take lots of shapes too, although not all of them are true crystals. Glass is an enormously important example of a three-dimensional silica-based amorphous solid. It's worth mentioning here even though it's not a crystal because its molecular structure is extremely similar to the structure of quartz, just not as orderly. The arrangement of silicon and oxygen atoms in quartz is very regular and rigid. The molecular structure of glass, on the other hand, looks like Mother Nature tried to build a quartz crystal while she was a little bit drunk. The atoms are attached in random numbers and shapes, creating a fragile structure with no definite order. This is why glass can be formed into almost infinite shapes when it's heated, while quartz keeps its characteristic crystal shape. Because it's an amorphous solid with bonds of varying strength, glass doesn't have an exact melting point. Instead, it softens as it's heated and becomes like honey-like, except extraordinarily hot and not sweet at all. Quartz doesn't do that. Its melting point is much higher, but it melts at an exact temperature and has no pliable in-between state. Like all silicon crystals, quartz, glass, and ceramics are electrical insulators because they have no free electrons to transfer charges over a distance. The atoms have 4 valence electrons and they form 4 bonds, so all the electrons are perfectly well used. For this reason, these materials are used widely as insulators in electrical applications. Ceramics, for example, are used to hold live wires and power lines and to make capacitors, which are basically layers of electrical conductors separated by layers of insulator. But all these silicon-based network solids I've talked about so far contain both silicon and oxygen atoms. Crystals made up of silicon are insulators too in their pure state, but they can be made to transfer electricity by a process called doping. And no, we're not going to make a Lance Armstrong joke. We might make an analogy though. It's like much like a perfectly fit athlete injecting himself with all kinds of weird foreign stuff. Silicon doping involves incorporating impurities into a crystal that mess up its electron balance. It can do that in one of 2 ways. If the impurity is an element with more electrons than silicon has, like phosphorus or arsenic, the resulting crystal will contain excess electrons. But if the impurity is an element with fewer electrons, like aluminum or boron, it leaves holes where electrons are missing from the normal structure. Doped silicon crystals are known as solid-state semiconductors. Those doped with elements that add electrons are called n-type or negative semiconductors because of the resulting charge from the addition of electrons. With n-type semiconductors, the charge is carried by the excess electrons, and because there's no room for them to integrate into the structure, they move freely about the crystal. Similarly, crystals doped with elements that create an electron deficiency are called p-type or positive semiconductors because they have a more positive charge than pure silicon would have on its own. P-type semiconductors work a little differently. Because they have empty spaces available here and there, the electrons that are normally part of specific silicon atoms are able to jump around from one atom to another. Each jump fills a hole and creates a new one, allowing another electron to move in the same way. So if both n-type and p-type crystals are both electrical conductors, why do we call them semiconductors? Well, thank you for asking. The reason semiconductors are so valuable is that they have the amazing ability to conduct electricity freely under some conditions, but completely refuse to conduct it under other conditions. So yes, they are partial or semiconductors. So these properties become most useful when a p-type and n-type semiconductor are placed next to each other to form a diode. Because their charges are opposite, the free electrons in the n-type are attracted to the p-type and tend to migrate to its holes. And when an electrical field is applied to this arrangement so that the n-type is attached to the positive terminal, also called the anode, and the p-type is attached to the negative terminal or cathode, all of the free electrons are pulled completely into the n-type. These free electrons are attracted away from the holes, not into them, so any further motion is blocked and no more current passes through the diode. This type of arrangement is called reverse bias. However, just by reversing the polarity of the electron flow, if you will, we can create a very different situation. If the n-type side is attached to the negative terminal and the p-type side attached to the positive terminal, then the electrons are pulled into the p-type, making this part an electrical conductor again. This process, called forward bias, is self-perpetuating and allows the current to readily flow through the diode. The fact that this conduction only works in one direction is extremely useful. You know AC and DC, right? Back in black for those about to rock. AC is alternating current, where the flow of electrons alternates in one direction to the other. In DC, or direct current, is exactly what it sounds like. The electrons go directly where they're headed without backtracking. And simple arrangements of diodes can be used to convert AC to DC, like in this power supply for my laptop. P and n-type semiconductors can also be combined in sets of 3. These are called transistors, and they completely revolutionized the field of electronics, also the entire world, since they were invented in 1947. One of the main functions of a transistor is to switch an electrical signal on and off. Basically, when it allows the current to flow in the forward bias direction, the switch is turned on. When the current drops below the minimum, the switch is turned off. This switching is the basis of binary code, ones and zeros representing the on and off states of the transistor. And that code is how we store and process information using computer chips, which are just collections of transistors working together. Such a tiny, simple device made mostly from one single element and yet revolutionizing our entire world. That, my friends, is how Silicon Valley got its name and how network solids of silicon made this conversation we are having today possible. Thanks for taking advantage of all your tiny transistors today by watching this episode of Crash Course Chemistry. If you paid attention, you learned that sand and glass and
Maxi presents turning beach sand into pure silicon dioxide. So what we want to start with is 150 grams of sand. Okay, as you can see, we take some HCl and measure out about 100 milliliters of it. So now we transfer the HCl to a hot plate stirrer, and we're going to dissolve the sand's impurities into the HCl, one of them being calcium carbonate. And this will produce carbon dioxide gas, so you're going to want to do this, you're going to want to add the sand slowly. We also add a boiling flask to condense the HCl vapors. Now that we have our acidic sand, we just wash it with water. And here's a time-lapse of me washing the sand. We want to get it to, obviously, about pH 7 to get rid of all the acid residue. Here's a little intermediate product of crude silicon dioxide with some black dots in it. Now what we need to do is we need to transfer this to a pure plate and dry it. We need to dry this because we have a step that involves reacting it with sodium hydroxide. So here's a purified sand when it's dried. And our yield is about 140 grams of the crude silicon dioxide. Okay, so the way we're going to purify this sand into pure silicon dioxide is to start by weighing 80 grams of sodium hydroxide out on a scale. Next, we want to transfer it to a stainless steel crucible because otherwise it'll eat through almost any other kind of crucible. I guess you could do it in a copper pot, I guess, but who has those, right? Anyway, we transfer 60 grams of our crude silicon dioxide to the crucible and mix it in with the sodium hydroxide. Next, we just heat it up, and we have to make sure that it gets above 330 degrees Celsius so that the sodium hydroxide can mix into the sand and react with it to form sodium silicate. And I'll tell you what we're going to do with that to form silicon dioxide later. Here it is, after it's been on the heat a little bit. The sand may look like it hasn't dissolved yet, but eventually it all will. So here it is when it's almost stiffened up and almost all the water's gone. And now to get it out, you sort of want to get it out quick because it hardens like glass, and I had to use a hammer eventually. So now we just transfer all of our product, our sodium silicate and excess sodium hydroxide, to a beaker, and we dissolve it in about 400 milliliters. Do your best, because it's a little hard to do. Next, we just gotta filter it to filter out the insoluble impurities. and transfer it to a vessel that you don't really care about, as this will heat up and the silicic acid formed will stick to the glass. Now we just measure out 25 milliliters of sulfuric acid and drip it into the solution slowly. Listen to the sound. This is really cool. So what's happening is actually it's forming a gel, which is a sort of gelified complex of silicic acid, and it's sort of unknown whether or not the silicic acid will decompose into silicon dioxide on this step. We could very well still have silicic acid, so our next step will be filtering it. Okay, so here it is transferred to a filter setup, and we just wash it with water. And I transferred it to a toaster tray, and now I'm going to load it into the toaster on toast, and that's probably about 475 degrees for around 25 minutes. So here's our crumbly and rocky product that I'm just going to break up now. So our yield is about 40 grams of the silicon dioxide, and our yield was about 57%. Now, what are we going to use this for? We're going to use it to make silicon dioxide thermite, and also to make magnesium silicide. And I hope you guys know that I'm really thankful for all your support, and thanks for watching. Bye!
This episode is supported by Prudential. So it's Friday, April 21st, 1820. A physics professor in Denmark named Hans Christian Ørsted is in the middle of a lecture.
So you can say computation is capturing patterns in reality through the flow of electromagnetic field, through manipulating the flow of the electromagnetic field. You can have spontaneous computation as well. Maybe not. No. It depends on what you're defining computation as. If it is the transfer, if it is related to information, then I think it can't happen spontaneously. It should be manipulated by something. But even that is a more deeper question, because even if it is manipulated by something, that something is still the universe itself. So when they become someone. So yeah. Not sure.
And he's using a compass and an electric wire for a demonstration. He turns on the current that runs through the wire, and he notices that the needle in the compass starts to move. And when he turns the current off, the needle moves back to where it was. Then he runs the current through the wire in the opposite direction and sees the needle move the other way. What Ørsted demonstrated that day was a fundamental discovery, the connection between electricity and magnetism. And it changed the field of physics forever. The relationship between electricity and magnetism not only explains what Ørsted and his students witnessed in 1820, it also makes possible much of the technology that's used today, from hydroelectric dams to your smartphone. It even explains why Earth's magnetic field is essentially keeping you from being cooked alive right now. And all you really need to understand the basics of magnetism and electricity is this. Magnets. It depends on their molecular properties, and other metals including cobalt, nickel and iron are attracted to magnets, even though they aren't magnets themselves, like the metal in your refrigerator door. And there's a magnetic field around Earth, which is why you can use a compass to figure out which way is north. The magnet in the compass aligns itself with the Earth's magnetic field. Just as we use electric field lines to represent the electric field created by charges, we can draw magnetic field lines to represent magnetic fields created by magnets. And as with electric fields, the more crowded the lines are, the stronger the magnetic field. The lines point from the North Pole to the South Pole, like how electric field lines point from the positive to the negative charge. But there's a key difference. You can have an electric field spreading outward from a single electric charge, but that can't happen with magnets, because you can't isolate one magnetic pole. If you chop a bar magnet in half, you don't end up with one north magnet and one south magnet. You end up with two magnets, each with its own north pole and south pole. This means that the magnetic field lines surrounding a magnet always form closed loops. We measure magnetic fields using a unit called the Tesla, which is 1 Newton per ampere meter, and 1 Tesla is a very strong magnetic field. The fields from some of the strongest superconducting magnets in the world are only 10 Teslas. Now, when Ørsted was doing a demonstration on that fateful day in 1820, he was using a regular compass magnet, but when he brought the magnet close to a wire carrying a current, the magnetic field from the current exerted a force on the needle, moving it to point in a different direction. Ørsted had discovered one of the fundamental principles of electromagnetism. An electric current produces a magnetic field. After a few more months of experimenting, Ørsted figured out that when a current runs through a wire, the magnetic field that it produces surrounds the wire. Expressed with field lines, the magnetic field would appear as circles with the wire at their center. If the current was coming straight towards you, the field lines would be pointing counterclockwise. And we use the vector B to represent the magnetic field, the magnitude of the vector running through a wire. And it does, which is good because it's out too. But you'll have to, and in that case, there won't be any magnetic field does to the charged particles coming from the sun. It deflects them, sending them spiraling away and protects applied to a single. These two stronger the closer to perpendicular the charge's velocity is to the magnetic field lines, which means that if the charge's velocity is parallel to the magnetic field lines, there won't be any force on it whatsoever. Second, the more charge the particle has, the stronger the force. And third, the faster the particle is moving, the stronger the force.
If there's a relationship between magnetism and electro fields. Maybe there is a relationship on the complex plane. There it is, this is sure.
Finding the direction of this force is where the third right-hand rule comes in. So get your right hand out again, straighten your fingers with your thumb stretched outward, then point your arm in the direction of the particle's velocity.
No, electricity is usually calculated using the complex field, if I'm not mistaken, so there's definitely a relationship there.
Then bend your fingers to make them point in the direction of the magnetic field lines. This is where things get a little tricky. If the charged particle is positive, your thumb is pointing in the direction of the force. But if it's negative, the force is pointing in the direction opposite your thumb. So electric currents create magnetic
complex fields,
and magnetic fields exert forces on electric currents and charges. Ersted experiment was simple, but his discovery linked two major fields of physics and inspired other scientists to do a lot more experimenting. Today you learned about magnetism and
The FinFET is a radical new transistor architecture that is difficult to visualize and understand. This video is designed to demystify the FinFET structure and make it readily comprehensible to those who've never seen it before. We begin with a classical MOSFET transistor, displayed in this cutaway view. It consists of the standard elements: the source, the drain, the gate electrode, the polyoxide, the nitride spacer, the shallow trench isolation, the well, and the gate oxide. The short dimension of the gate electrode is called the length. The long dimension is called the width. When the gate electrode is energized, an electric field is established that inverts the channel, forming a conductive pathway from the source to the drain. However, as the length of the gate electrode is reduced, the control of the gate over the channel region is also reduced. This lowers transistor performance. The FinFET is designed to address this performance shortcoming by wrapping the gate electrode around the channel instead of having it lay on top of the channel, as in the case of the classical transistor. In the FinFET architecture, a thin fin of silicon acts as the channel, and it is encased by the gate electrode. The source and drain are those regions of the fin that are not covered by the gate. End and on, the source-drain regions consist of an undoped silicon fin surrounded by an extension implant and polyoxide. A cutaway view reveals...
Close this. In 87, the French chemist Antoine Laurent de Lavoisier first discovered the silicon present in rocks. In 1800, silicon was mistaken by Sir Humphrey Davy as a compound. In 11, French chemists Joseph Louis Gay-Lussac and Louis prepared impure amorphous silicon by heating potassium with silicon tetrafluoride. He later named it silicon according to the Latin silex. Till 23, silicon was first discovered in the form of a metal element by the Swedish chemist. This name here. 1 year later, he extracted amorphous silicon much the same way as Gay-Lussac, and then purified the elemental silicon by repeating cleaning. The same year, he heated the silicon oxide powder and the mixture of iron and carbon at a high temperature and obtained the iron silicide. In order to extract polysilicon, dry fire the silicon fluoride calcium compounds, hydrolyze the obtained solid, and managed to obtain the pure silicon. 24, in Stockholm, Berzelius obtained relatively pure silicon powder by heating potassium fluoride and potassium. Therefore, it is agreed that the honor of discovering silicon belongs to Berzelius. Silicon, yeah, interesting.
Only a few elements can be permanent magnets. Iron is one. Copper is not. But if you pass an electric current through any metal, it becomes a magnet. An electromagnet. But how does this work? Well, strangely enough, it's a consequence of special relativity.
Special relativity is the fact that in our universe, length and time aren't absolute. They're perceived differently by observers moving relative to each other, hence relativity. For example, if you measure carefully enough, you'll find that time passes slower for observers moving relative to you. Hey Derek, when did you last shave?
6 hours ago. Actually, it was 5 hours, 59 minutes, and 59.999999999 seconds.
And moving objects are also contracted in their direction of motion.
You're looking slim, only in your frame of reference. So when an object is moving relative to you, it actually takes up less space than when it's not moving. And even though this effect is obviously way tinier than we've shown, length contraction is what makes an electromagnet work. Picture a copper wire. It consists of positive metal ions swimming in a sea of free negative electrons. Now the number of protons is equal to the number of negative electrons, so overall the wire is neutral. So if there were a positively charged cat nearby, it would experience no force from the wire at all. And even if there were a current in the wire, the electrons would just be drifting in one direction, but the density of positive and negative charges would still be the same, and so the wire would be neutral, so no force on the kitty. But what if the cat starts moving? Imagine, for simplicity, that the cat is moving in the same direction as the electrons with the same velocity. Well, now, in my frame of reference, the wire is still neutral, and so there should be no force on the cat. But consider the same situation in her frame of
didn't realize
reference.
I was watching with the thing. Yeah.
In the cat's frame of reference, the positive charges in the wire are moving, so according to special relativity, their separation will be ever so slightly contracted. Also, from this perspective, the electrons aren't moving, so they'll be more spread out than before. Remember, objects take up more space when they're not moving than when they are. These two changes together mean there's a higher density of positive charges in the wire, so it's no longer neutral, it's positively charged, which means that the positively charged cat will feel a repulsive electric force from the wire.
But in my frame of reference, this seems mysterious. There's no force on a stationary charged cat, but a moving cat is somehow repelled from this neutral wire. How do you account for that force? Well, we say it is the magnetic force. And that's mainly because a wire with current in it deflects nearby magnets. So really what this experiment shows is that a magnetic field is just an electric field viewed from a different frame of reference. In the cat's frame of reference, it is repelled from the wire due to the electric field created.
Damn, this is... I'm gonna think about this one a lot. What's wrong with this? Whatever. Magnetic field is just an electric field viewed from another reference frame. Maybe I can write here.
By the excess positive charges produced by the effects of length contraction. In my frame of reference, the cat is repelled from a neutral wire due to the magnetic field created by the current flowing in the wire. So whether you see it as an electric or a magnetic field just depends on your frame of reference, but in either case, the results are the same. So an electromagnet is an everyday example of special relativity in action. Now that might seem crazy, since electrons drift through wires at about 0.00000000001% the speed of light. So how can special relativity have anything to do with it? Well, the truth is there are enough electrons in a wire, and the electric interaction is so amazingly strong that even the minuscule effects of length contraction can produce significant charge imbalances that produce a noticeable force.
So special relativity explains electromagnets, but what about permanent magnets?
Yeah, I mean, there can't be electrical currents flowing around inside lumps of rock, can there? Click here to go to Minute Physics, where we'll explore magnetite, compasses, and...
If you think Maxwell's equations describe all of electromagnetism, then you're missing half the picture.
This episode was made possible by generous supporters on Patreon.
Hey crazies, we spent the better part of the 1800s trying to figure out how electromagnetism worked. To the timeline! In 1820, we got Ampere's law. In 1831, we got Faraday's law. In 1835, we got Gauss's...
I think I'm gonna take a picture of this, actually. So I can research later. The problem is I don't know how to... Don't know how to write this on the computer.
law. In 1861, Maxwell added some stuff. And finally, in 1885, Heaviside wrote out all four in the form we know today. They're called the Maxwell-Heaviside equations, and they govern the behavior and appearance of electric and magnetic fields. But I spent the entire last video visualizing those four laws. This video is about the fifth law. Wait, what fifth law? The Lorentz force law. It tells us what those fields do. They exert forces. See, things like magnets and charges can exert forces on each other over a distance. That kind of seems like magic, which is a problem. These two fields are a way for us to avoid that problem. They act kind of like a middleman or intermediary. One charge creates a field, and it's that field that actually exerts a force on the other charge. The whole purpose of those fields is to explain force at a distance. But the Maxwell Heaviside equations only tell us how fields are made. It's the Lorentz force law that shows us how those fields affect things. They each only tell half the story. You can't understand electromagnetism without all 5 of them. And as it turns out, those don't even make complete sense without special relativity. Just like the field comes in 2 parts, electric and magnetic, the force comes in 2 parts, an electric force caused by the electric field, and a magnetic force caused by the magnetic field. This velocity is going to be the source of our troubles. We've known since the time of Galileo that motion is relative. I demonstrated this a long time ago with a tennis ball in a car. Actually, that reminds me, whatever happened to chauffeur clone? Oh well, he'll turn up eventually. Anyway, if this force has a velocity in it, that means it's also relative to the observer, which is fine most of the time, but in certain circumstances, it could become an issue. Let's take a look at one of those circumstances. Full disclosure, I didn't come up with this example myself. It's from the Feynman lectures, link in the doobly-doo. I also did a video on it a long time ago, which was funny, but not very informative. I can do better. Say we've got a conducting wire made of loosely bound electrons held in place by some positive bits. Yes, it's technically more complicated than that, but it's good enough for today. The wire is electrically neutral. There are just as many positive charges as there are negative charges. So Gauss's law tells us there's no electric field. But let's say somewhere down the line we hook up a battery. That gets the electrons moving. The wire is still electrically neutral, so no electric field. However, we know from Ampere's law that around any moving charge, we'll find a magnetic field. This wire has a magnetic field that wraps around it. Now that we've got a field, we should be able to exert a force on something. In this case, it's a magnetic field, so we should get a magnetic force. It'll be exerted on anything that has a charge and is moving. Shrink ray time! Let's say this squirrel is positively charged and moving to the right at the same pace as the electrons. We've got a charge in motion inside a magnetic field. That means there's a magnetic force. The squirrel is repelled from the wire. No problem so far, everything is fine and dandy, until we switch points of view. This is what we might call the lab frame. It's the point of view of everyone in my lab who has their feet firmly on the ground. But what if I have a clone on a treadmill moving along with the squirrel? Instead of this, he'll see something more like this, which we'll call the clone frame. There's a state. If the squirrel is repelled in one of them, it must be repelled in the other. That can happen a slightly different way or even for a different reason, but it must happen, from all points of view. Thankfully, Einstein's special relativity can fix this problem. It's really good at handling shifts in point of view like this. According to the model, there are only a few things that stay the same under these shifts. Charge is one of them. Everything else is relative. That means they change under these shifts. The one we'll be taking advantage of today is length. As you shift from one point of view to another, the length of objects can change, and so can the distance between them. They don't just appear to, they actually do, like for real. How much they change depends on how much your point of view has shifted. The shift here isn't very big, but it's still enough to fix our problem. I'll exaggerate everything for the rest of the video so you can see what's happening. In the lab frame, the squirrel is moving, so it's contracted along that direction. Everything in the wire is fine, it happens to be neutral in this frame. Just like before, the magnetic field around the wire exerts a magnetic force on the squirrel, repelling it away. In the clone frame, things look a little different. The squirrel and electrons are stationary, so they're not contracted anymore. Now that the positive bits are moving, they are contracted. That means this part of the wire has a net charge. Density. Charge may be invariant, but space is not. Charge density is the amount of charge divided by the space that charge occupies. In our case, we're measuring that space as a distance. The electrons have expanded and the positive bits have contracted, which means they occupy a different amount of space. Their density has changed. Each spot along the wire has a net positive charge. According to Gauss's law, that means there's an electric field. If there's an electric field, the Lorentz law tells us there's an electric force. Bingo bango, we've got a force. In the clone frame, the squirrel still repels from the wire. It's just due to an electric force instead of a magnetic force. Whew, crisis averted. Thanks, Einstein. Like I said though, the total amount of charge is still invariant. If you look at the whole circuit, you can see what's really happening. While we have a net positive charge near the squirrel, the segment farther away has a net negative charge. The charge has just redistributed. The point is, special relativity fixes our problem by making the following statement. The magnetic force in one frame of reference could easily be an electric force in another, or some combination of them in a third frame. We can show this in the Lorentz force law by pulling out be able to say it in 4 columns, because there are 4 dimensions in spacetime. It represents the electromagnetic field as a field of tensors. One tensor at every point in space and every moment in time. It groups the electric and magnetic fields together in just the right way, so the Lorentz force law still works out the same. We even get electrical power as a bonus. So how does special relativity fix electromagnetism? By allowing measurements to change between points of view. In the lab frame, the moving electrons use the magnetic field to exert a magnetic force on a squirrel. In the clone frame, the electrons expanded and the positive bits contracted. This left the wire charged, allowing it to exert an electric force instead. The squirrel was repelled by the wire in both frames. Sometimes magnetism is just electricity in a different frame of reference. So hopefully this version of the video makes a lot more sense. Let me know in the comments.
Hi, I'm Bob Duhamel, and I'm going to explain the relationship between electricity and magnetism. And that relationship is, they're the same thing. So here's the deal. Let's say I take a battery, and I'm going to hook up a wire to it with a switch, so I can switch the...
You wanna watch this one last?
Today I want to explain how we know that the way Einstein thought about gravity cannot be correct. Einstein's idea was that gravity is not a force, but it is really an effect caused by the curvature of space and time. Matter curves space-time in its vicinity, and this curvature in return affects how matter moves. This means that, according to Einstein, space and time are responsive. They deform in the presence of matter, and not only matter, but all types of energies, including pressure and momentum flux and so on. Einstein called his theory general relativity because it's a generalization of special relativity. Both are based on observer independence, that is, the idea that the laws of nature should not depend on the motion of an observer. The difference between general relativity and special relativity is that in special relativity, space-time is flat, like a sheet of paper, while in general relativity it can be curved, like the often named rubber sheet. General relativity is an extremely well-confirmed theory. It predicts, for example, that light rays bend around massive objects like the sun, which we have observed. The same effect also gives rise to gravitational lensing, which we have also observed. General relativity further predicts that the universe should expand, which it does. It predicts that time runs more slowly in gravitational potentials, which is correct. General relativity predicts black holes, and it predicts just how the black hole shadow looks like, which is what we have observed. It also predicts gravitational waves, which we have observed, and the list goes on. So there is no doubt that general relativity works extremely well. But we already know that it cannot ultimately be the correct theory for space and time. It is an approximation that works in many circumstances, but fails in others. We know this because general relativity does not fit together with another extremely well-confirmed theory, that is quantum mechanics. It's one of these problems that's easy to explain but extremely difficult to solve. Here's what goes wrong if you want to combine gravity and quantum mechanics. We know experimentally that particles have some strange quantum properties. They obey the uncertainty principle, and they can do things like being in two places at the same time. Concretely, think about an electron going through a double slit. Quantum mechanics tells us that the particle goes through both slits at the same time. Now, electrons have a mass, and masses generate a gravitational pull by bending space-time. This brings up the question, to which place does the gravitational pull go if the electron travels through both slits at the same time? You would expect the gravitational pull to also go to two places at the same time. But this cannot be the case in general relativity, because general relativity is not a quantum theory. To solve this problem, we have to understand the quantum properties of gravity. We need what physicists call a theory of quantum gravity. And since Einstein taught us that gravity is really about the curvature of space and time, what we need is a theory for the quantum properties of space and time. There are two other reasons how we know that general relativity can't be quite right. Besides the double-slit problem, there is the issue with singularities in general relativity. Singularities are places where both the curvature and the energy density of matter become infinitely large. At least that's what general relativity predicts. This happens, for example, inside black holes and at the beginning of the universe. In any other theory that we have, singularity are a sign that the theory breaks down and has to be replaced by a more fundamental theory. And we think the same has to be the case in general relativity, where the more fundamental theory to replace it is quantum gravity. The third reason we think that gravity must be quantized is the trouble with information loss in black holes. If we combine quantum theory with general relativity but without quantizing gravity, then we find that black holes slowly shrink by emitting radiation. This was first derived by Stephen Hawking in the 1970s, and so this radiation is also called Hawking radiation. Now it seems that black holes can entirely vanish by emitting this radiation. Problem is, the radiation itself is entirely random and does not carry any information besides the temperature. So when the black hole is entirely gone and all you have left is this radiation, you do not know what formed the black hole. Such a process is fundamentally irreversible and therefore incompatible with quantum theory. It just does not fit together. And a lot of physicists think that to solve this problem, we need a theory of quantum gravity. So this is how we know that general relativity has to be replaced by a theory of quantum gravity. This problem has been known since the 1930s. Since then, a lot of attempts have been made to solve it. I will tell you about this some other time, so don't forget to subscribe.
First glance, the laws of electromagnetism appear to violate Einstein's theory of relativity, which states that it's not possible to tell if you're moving or if you're standing still. According to Maxwell's laws of electromagnetism, two particles with the same charge moving in the same direction will exert an attractive magnetic force on each other. This occurs only for moving charged particles and not for stationary charged particles. From Sarah's point of view, the two charged particles are moving, and they will exert an attractive magnetic force on each other. From Adam's point of view, the two charged particles are standing still, and there's no magnetic field and no magnetic force.
I think the bigger question is why some things attract themselves and others repel.
How is it possible to reconcile the two views?
If everything is motion, then magnetism and electricity are the same thing. How is it possible that they are different? They attract and repel based on the configuration.
Use. Although Adam and Sarah will disagree about if there is a magnetic field present, they will both agree that there are electric fields present. All charged particles create electric fields, regardless if they are moving. Adam and Sarah will agree that the electric fields cause the two particles to repel each other due to the fact that the two particles have the same charge. In addition to the repulsive electric force, Sarah will also see the attractive magnetic force. Sarah will see the repulsive electric force as stronger than the attractive magnetic force. Therefore, she will still see the two particles move away from each other, but she will see them move away from each other slower than they would if there was no magnetic field present. But Sarah will not be able to use this as evidence to convince Adam that he's moving. This is because Sarah will see Adam's clock running slower than her own. When Adam uses his clock to determine how fast the particles are moving away from each other, he concludes that it's at exactly the rate as if there was no magnetic field present. Hence, all of Adam's observations remain consistent with his belief that there is no magnetic field present and his belief that he is standing still. Einstein's theory of relativity has therefore not been violated. But let's try to violate Einstein's theory of relativity in a slightly more clever way by introducing gravity into the picture. Suppose we prepare two charged spheres.
What I need to do is understand quantum mechanics and go through the playlist of relativity first of the tensors and try to code along the videos so I understand better how it works.
The gravitational field that we normally think of around an object with mass is analogous to the electric field around an object with charge.
It's too hard to get all these things and relate them to social dynamics and social structures.
We can also think of a new type of gravitational field created by a moving mass that is analogous to the magnetic field created by a moving charge. Sarah will see
current on and off. Run that wire over here and back to the battery. And I'm going to put a compass near this wire. I'm just going to show the compass needle across the wire. I'll just show it as an arrow. And where's that compass going to point? Of course, it's going to point to the Earth's North Pole, as compasses do. But if I close this switch, that compass will turn and line up perpendicular to the wire. And then if I open the switch, the compass needle will turn back to the Earth's North Pole. So this demonstrates that there is definitely a relationship between electrical current and magnetism.
This is the last video I will watch today. It's already late here. Tomorrow I'll probably go over these topics. I haven't even started this one yet. Well, this one I feel like I covered today. So I'll go through the other ones.
Because when I have the current flowing from positive to negative, that's called conventional current, for those of you who know about the electrons. If I have a current flowing through the wire, the needle lines up perpendicular to the wire. But if I turn off the current, the needle no longer reacts to the wire. So obviously a connection between electricity and magnetism. Now if I take two wires, run them parallel to each other, and now let's hook up batteries to those, so I have the positive side here and the negative side here. So I now have an electrical current, let's say conventional current, running in this direction in the two wires. Those wires will attract each other. And if I flip the polarity on one of the wires, so that the currents are running in opposite directions, now the wires repel each other. And this further shows the connection between electrical current and magnetism, because if I take an electroscope or some other device that can measure electric fields and put that electroscope near these wires, it doesn't react. but yet they are reacting to each other. So it shows that this effect of the wires repelling each other when the currents go in opposite directions and attracting each other when the currents go in the same direction is magnetic, not electrical, because the electroscope doesn't detect any electric fields in the wires that could account for the attraction or repulsion. So the deal is, when I have an electric current flowing through a wire, there is a magnetic field around it. When there is no current flowing, there is no magnetic field. So what's going on here? To understand that, we have to take a look at the molecular structure of the wire. So a copper wire consists of gazillions of copper atoms, and each one of those copper atoms consists of 29 protons in a nucleus, and around those 29 protons are orbiting 29 electrons. And these electrons are orbiting in rings or shells where the 28 electrons are in the inner shells, but the very last shell, the most outer shell, has that 29th electron. This is the nature of metals. Metals usually are those materials that have 1, 2, or 3 electrons in the outermost shell of electrons. There are some exceptions, such as tin, lead, antimony, and arsenic, which have more electrons, but most metals...
And can view any object or matter as a scale of the electromagnetic field, because that's how we differentiate things based on how much charge they have, which gives them different geometrical properties and molecular structures. So everything, in a sense, is electromagnetic field in relationship to space-time.
have 1, 2, or 3 electrons. And when metals form a mass, they form a structure where those electrons disassociate from the atoms. So what I have in this mass of copper, and I'll draw these atoms on one side just to facilitate how I'm making the drawing. These atoms, of course, are all through the wire, but I just need room to draw something else here. So I have a bunch of copper atoms in a copper wire, and each one of those atoms, because of the nature of metallic bonds, is a positively charged copper ion. And for each positively charged copper ion, I have an electron that is floating around nearby it. And the nature of the metallic bond is that the electron does not tightly fit into this matrix, so it is free to move around. These positive ions are locked into the matrix, so they can't move, but the electrons can move around freely.
I think a good question is, what would be the charge of social structures? As it scales and in all levels of perception. What would that mean? What's the geometry of tribalism?
So let's put a voltage across here and make those electrons move. So negative on this side, positive on this side, I just simply have that hooked up to a battery, and the electrons are repelled by the negative charge and pushed toward the positive charge. So the electrons are moving in that direction. So how does this produce a magnetic field? To understand that, we have to take a look at special relativity. And according to special relativity, if I have an object, I'll just have maybe a yardstick here, or a meter stick for most of the civilized world. We'll make this 1 meter long. It could be a yardstick, it could be a piece of metal, it doesn't matter what it is, it's 1 meter long. And if relative to me it's not moving, it looks like it's 1 meter long. But if I give it a push and make it go that way, or either I'm going this way and it's holding still, either way I see relative motion and I see it moving that way, and I measure it, it's ever so slightly shorter. This is called length contraction. And normally this effect is not discernible unless we get something up somewhere near the speed of light. So the common wisdom is we can't observe this length contraction under any kinds of speeds that we can observe ourselves, only things that can get up near the speed of light. But nevertheless, when things move, the length does contract, and that goes for objects moving too. So if I have a line of objects all lined up, whether they're rocks, asteroids, or electrons, if they're holding still, let's say they're that far apart. But if they move, thanks to length contraction or Lorentz contraction and special relativity, they're slightly closer together. So if I see a bunch of objects move, they are closer together. So now, when these electrons move, there's more electrons per inch in the wire than when they're stationary. So now, if I put another wire over here, and it's doing the same thing, let's put our metal ions here. And let's turn off the power for a moment. So now the electrons are not moving, and the electrons are so far apart. But now let's put the voltage here. Now these electrons are moving. Now that they're moving, they're slightly closer together, and so I see more electrons per inch than if they weren't moving. Now, it's very, very slight, but there's so many electrons that the effect is cumulative, and I do see an effect. So I see more electrons per inch when they're moving than when they're not moving, and the same thing happens down here. So now that they're moving, there's more electrons per inch than when they're not moving. So these positive ions here see more electrons per inch in this wire than they do positive ions in the wire, so they see a negative charge, and so the positive ions are attracted towards the electrons, and that pulls this wire towards that wire. And of course over here I see the same thing. These stationary positive ions see the moving electrons over here. They're moving, so due to special relativity they're slightly closer together. More electrons per inch than positive ions per inch. So these positive ions see more electrons.
So you can say that magnetism is just a transformation of electricity in reference frames. So which is the same thing that happens when on the complex plane. Just see the input and output of functions. It's very interesting.
Over here, and so they're attracted to that concentration of electrons, and so this wire is pulled the other way. So that is why the wires are pulled towards each other. But there's a slight problem to this. I'm standing here stationary looking at this, and I see the electrons moving, so those electrons are ever so slightly closer together, so I see more electrons per inch too, as well as the ions. So if I take that electroscope and I move it toward these wires, I should see a negative charge. Why don't I? I can explain this with a weekend of golf. So let's go to the golf course, and the first day we get to one of the greens, and there's the hole, and this hole on the green has an attractive force towards golf balls. We know that because golf balls tend to end up there. And so we go to the green, we put out, and we move on. The next day, I come back to the same green, and as often happens, they moved the hole, just to keep things interesting. So that attractive force to those golf balls moved from here over to here. Did that hole move? Of course not. The hole is nothing. A hole can't move. What they did is they took a plug of dirt from here and moved it into the hole there, leaving a hole on this side. So the hole disappeared here and reappeared there when the dirt went the opposite direction. However, I can't tell the difference. I can't see the hole move. All I know is that the force that attracts golf balls moved from here over to here. So I saw the movement. And although that is not really a movement of anything in this direction, my perception is that it did move. And that perception, when it comes to special relativity, is just as real as the real movement of an object. So if we go back to the wires, let's look at our first wire here. Once again, there's our electrons. Here's our positive ions. And the electrons are moving in that direction because I have a negative charge applied there and a positive voltage applied there. The negatively charged electrons are moving that way. And as these charges move, they are moving past these positive ions, which are positive ions. Why? Because I pulled an electron away from them. Just like the hole in the golf course, there's a hole there because I took some dirt out. These are positive ions because I took electrons out. As a matter of fact, physicists call the charge left behind in an ion because of the removal of the electron a hole. So I see the electrons moving this way, and although these positive ions are stationary, I see the positive charges moving the opposite direction. And even though the charges are not really moving, even though it's purely perception, that motion is still subject to special relativity. So I see the electrons moving this way. Because they're moving, there's length contraction, they're closer together. I see more electrons per inch when they're moving than when they're stationary. Also, the positive charges are moving the opposite direction. So due to length contraction, they are closer together, and I see more positive charges per inch. So from my stationary point of view, I see the electrons moving one way, more electrons per inch, but I see the positive charges moving the other way at the same speed, so I see just as many more positive charges per inch. And if I bring that electroscope up here, it's not moving, so it sees the same thing. It sees the electrons going one way, the positive charges going the other way, more electrons per inch, but also more positive charges per inch, same number of electrons as positive charges, and it sees no electrical effect. But what do the electrons see? Well, have you ever been stopped at a traffic light and you're waiting for the light to turn green and the car next to you starts to roll backwards and you see it moving backwards and you think you're rolling forward, so you press harder on the brake only to find out it was them moving and not you. Or perhaps you started to roll forward a little bit and you see them moving out of the corner of your eye and you think, oh, that car is moving backwards, only to look up and see, oh my gosh, it's me moving, and then you do stop. The point is, you didn't know you were moving until you saw other clues to tell you you were moving. So you always think that you are not moving, and if you actually move and see something else go by, you think that it is moving, not you. So these electrons are moving in this direction, but they don't know they're moving. They're all moving the same direction at the same speed. They don't know they're moving. They have no other clues, so they are not subject to the length contraction. So the electrons see themselves as spaced normally. But what do these positive charges look like? Well, they're zipping by in the opposite direction. So the electrons don't feel like they're moving, but they see the positive charges moving, so to them, the positive charges are closer together. The electrons see more positive charges per inch than electrons per inch. But likewise, these positive charges are moving in the opposite direction. What do they see? They don't know they're moving. They don't see the length contraction. They think there's the normal number of positive charges per inch. But they look at the electrons, and the electrons are moving the opposite direction. They see the electrons closer together, so they see more electrons per inch. So, with the relative motion, what we see, I see the electrons moving this way, and the positive charges moving the opposite way at the same speed in opposite directions. I see the same number of electrons per inch as positive charges per inch. I don't see an electric imbalance. But the electrons see more positive charges per inch, and the positive charges see more electrons per inch. Now what happens if I put that second wire here?
It's really confusing. It's just that the way that people represent the magnetic field. That's why it's hard to understand.
But the voltages
But now I think I got it.
here. Here's my electrons. Here's my positive ions. Positive ions or positive charges moving that way, and the electrons moving that way. So what do they see? All these electrons are moving the same way in the same direction. They don't know they're moving, so they don't see themselves as closer together. But all these electrons look at all these positive charges moving the opposite direction, and they look like there's more positive charges. And so these electrons here see all these positive charges wire in the...
I think I'm done for today. I'll come back another time. When I do, I'm gonna start this course here. And later on go over the other topics. So see you then.